Hi, everybody, and welcome to this webinar on proposed changes to IS 456 and IS 1343. The current COVID-19 situation has challenged us in many ways. It has been a test of our patience, of our resilience, and our grit. And it's also been an opportunity to reflect on the way we conduct our lives, and in a way has revealed a reboot button should we want to use it. At SEFI, it has opened up the best possible path of engaging our community that is spread across the country. So now in real time, here we are, all sitting, listening to the same webinar. Originally, it was possible only for the few who were in Mumbai or able to travel to Mumbai to attend the seminar. But now, look, we have a full house. We have a capacity of 500 participants, and we are packed to capacity. So thanks everyone for such an enthusiastic response. I wanted to tell all the attendees and allay their fears that this code is already written, and so discussions really don't mean anything because typically what happens after the code is finalized, it's like my mind is made up, don't bother me with facts. But this situation is very different. The code is very much a work in progress. And so your feedback will go a long way in helping to take it to the next level. And God lies in details. And it is the practicing engineers who can really throw light on the nuances of the code as they experience it when they apply it. So before we dive into the seminar, I just wanted to share a few protocols and housekeeping issues. So just to talk about the schedule. In the morning, we are going to have a pre-lunch session, which will have 3 talks of 1 hour each by our resource persons. Between the talks, we will be having short breaks. This is to allow for any time overrun, and it also gives a breather to all of you to go get a cup of tea. And the duration of the break has been planned to be the first break being 20 minutes and the second one 10 minutes, but it may shorten or lengthen depending on the duration of each resource person's talk. The questions may be asked in the Q&A panel, which is at the bottom of your screen. We will not be using the chat option. And these questions and answers will be taken up in the post-lunch session. And in that post-lunch session, not only will we be taking up the questions you've raised in the morning, we will also take live questions, and you are encouraged to raise your hand and you can speak to everybody. I'm going to just display the schedule to you soon. And I know all of you know about it, but just as a recap. And I would just like you to note down all the comments you have, not just on the 3 talks and the content of the talk, but also about the webinar and what can we do to make it better and serve the community better. So we will be putting up evaluation forms on the website, and also each one of the attendees will be sent, and I would request you to fill it up. So now without much ado, I would like to call. So first, let me just for a minute, let me just share with you. Let me just share with you the schedule. If I know you all have it, but I'm just going to share the schedule with you. And let's see. Yes. Okay, so this is the schedule we have. You have at the first talk is of Professor V R Murty, which is up to 11. I'm sure we can give him the liberty to take 10 minutes more of the tea break if he needs to. Following Professor Murty's talk and the break, we will have Mr. Arora from NCCBM Ballabgarh, and he will be talking on issues of durability and materials. Post the second break, which is a 10-minute break. We'll have Professor Rupen Goswami talking about the design and detailing. After lunch, we will, I'm just going to be the post master, sharing all the concerns and comments on IS 456 from the SEFI discussions we've been having over the past 7 years. And then we start with the open house. So this is more or less what we are planning to do. And now to talk about, let me just share the screen with you, and let's just have Professor Murty's slide. And I think Professor Murty is no stranger to anybody. Everybody has seen one of the, what I consider one of the Bibles of earthquake engineering, which is the Earthquake Tips. And I think a lot of you also have seen this book called Earthquake Behaviour of Buildings and Earthquake Safety of for Building Contents, that is the non-structural elements. So Professor Murty is a fellow of the National Academy of Engineering, and he is the Institute Chair Professor at IIT Madras. He has been associated with major revisions of the Indian Seismic Codes and also for buildings and bridges. He's been responsible for development of a lot of guidelines for earthquake disaster mitigation for the National Disaster Management Authority. So without much ado, I'm going to hand you into the better hands of Professor Murty. Professor Murty, it's all yours. Go ahead. Yes, Professor Murty, you can go ahead.
Yeah. Namaskar, good morning, everybody, and welcome to this one-day excitement on the new Indian Concrete Code, which we are calling as the Structural Concrete Code. This is the second public consultation before the code is drafted. We did one in Visakhapatnam, and we were expected to do a round robin across the country before we freeze the code, and we are very happy that we have an opportunity to catch many of you in these moments of silence. And the second public consultation is supposed to be held in person. Now it's in a webinar mode. So we're going to discuss IS 456, the 5th revision, and then the IS 1343, the 3rd revision, as part of today's discussion on structural concrete code. So today's agenda overview of what's going to happen, which way are we going, major changes, from my side and from your side, that will be open-ended, and the afternoon is the most awaited section for us. You're aware that currently we are using IS 456-2000. It's a 4th revision, and so we are heading out for the 5th revision, and 1343 is the 2nd revision, and we are heading for the 3rd revision of 1343. So these are our two primary documents that are in focus for us. Let me take you through an overview of what's the road ahead. First of all, I'll start with motivation for this revision. Civil engineering structures are fortunate that we have to handle all the 5 elements of nature, and hence the design, construction, maintenance, all of it has to respect a comprehensive design approach and not just a piecemeal design approach. So that will be our first motivation why we needed to look at 456, because it was not giving us a holistic feeling so far. So we want to now go towards a holistic design approach, comprehensively addressing all the 5 elements of nature and their consequences on the built environment. Alongside, in the last 25-30 years, we also ran into a lot of excitement where a number of new typologies and structural systems were implemented without being admitted in the standard. These include the most exciting open ground story, the flat slab, even though we have some clauses, but the way flat slab is being done, post-tension slabs, particularly when we subcontract the slab design to somebody and the frame design to somebody, and these two somebodies don't talk to one buddy. And then the precast construction that's growing, the pre-engineered systems that are coming and the all-wall systems that are coming do not show up formally in the standard in the way we have them fresh in our minds, which tell us that we have lost sight of safety. So we need to bring safety back into the driving seat this time and keep emphasizing the vital role safety has to play in time ahead. So we will have a number of cautions and a number of precautions also for us. We need them because we cannot cross the line that are built across the country. You classify them under 4 categories. Those are in front of you. Today, if you ask me where are you in terms of a particular structure, I'm praying that somewhere we are in this range. But I also am aware that there are some structures that are sitting on the zone that we don't want. So this time, particularly, we would like to see that we can, if we can identify these structures, which are in the left 2 categories, that will be the ideal for us in terms of making sure that we have reduced vulnerability to the extent possible. At least the known vulnerabilities are removed. So these are some conscious decisions of reducing the shades of safety that we are practicing today. We would like to minimize that into a small corner towards the right, and that will be our agenda for code compliance in time ahead. Furthermore, if you look at today's design process, we choose materials, design sections, and go ahead and build. Whatever happens to the structure after that, we are not looking at it until the structure itself starts crying, which means that we have forgotten 2 more aspects of understanding the behavior of structures. Their overall resistance, their overall deformability has not been considered in our design process. So it's a one-way process that we are adopting, but what we require is a closed loop process, and hence we are seeking focus on overall behavior. And so we are now projecting towards or walking towards a closed loop design process where a designer knows exactly what has been proposed through the good for construction drawings. The next point that is in focus and has been in focus, and the only thing in focus has been cost. Every time we talk of structures, we want to reduce cost. Now, there are 5 aspects that you are looking at in a structure: safety, functionality, sustainability, aesthetics, and economy. Every time they want to affect economy, it is the first fellow, the safety, that is going a casualty. And this point, we would like to emphasize that actually there is a bottom line for minimum expectation from every structure. And the bottom line is safety, functionality, and sustainability. The only 2 negotiable items are aesthetics and economy. Now you have 2 options: aesthetics on the top or economy on the top. The first case is signature structures, where the owner will pay any amount just to make a statement. And the second case is all the rest of the structures, where aesthetics is not necessarily the focus. Well, if you can achieve within that, well and good, and that's what we're looking forward to. So the 6th motivation for us is this constant nagging discussion between economy and safety has to be clarified, that there is only one boss, and that is safety. Nobody else is on the top. One interesting fact I'd like to mention, 78% of India was born after this IS 456 was prepared. At least the design provisions were prepared in 1978. 2000, we didn't make much change in the design provisions. We added some on materials, but that's not large enough or significant enough like what we're doing this time. So I would say 78% of India was born after the standard is built. So we are a little worried that we have to now go and unlearn and learn. 78% of India has to learn and unlearn the new standard that we are coming up with, which means that it's in a participative mode that we can do it. And that is why we decided to have public consultations before we freeze the standard, because this percentage of people who are born after the standard are one too many. Also, I'm using the word market here consciously and not profession, because the materials that are coming out into the use are rising at a very alarming rate. And today from M20, M25, we have gone up to 120. as far as concrete is concerned, and from FE 415 we went up to FE 650. In this process, I also noticed that the market has decided itself to drop FE 415. There is a there's a marketing strategy here that strong is good, and so instead of giving you 415, I'm giving you 500. Why don't you use 500? That is the trap where most of the market has gotten into without understanding the implications. We have design provisions understood up to 550, but not 600 and 650. Also, design provisions understood up to about M40, M50, maybe M60 if you stretch as hard, but not M120. So this is the game that we are alarmed with, that without formal work, we are going ahead and using these materials for construction where the standard has not yet admitted these materials in. We are also looking at a number of other important features that our standards are keeping on. IS 456 keeps using this word characteristic load and characteristic strength of materials, but are we really doing characteristic? When you look at a review of all the loads that we have, some of them are mean and some of them are not characteristic. So there is a lot of formal work that we need to do in this front. So why am I saying all this? Because even though we'll come up with a standard this time, which is a little improvement over the previous one, I would still think that the formal work has to begin in the country. If we have 11 chapters in the new standard, I would like to see a group of people on each of the 11 chapters steering the agenda for the next 10 years and doing some deep R&D work and coming out with valuable inputs so that the subsequent revisions can stand on firm ground of self-reliance rather than peeping over the neighbor's windows. We also have a knowledge gap in terms of durability and design service life. There is a hesitation into nonlinear behavior, and rightfully so, but that hesitation has to be tempered, and we have to use them in instances where the design philosophy has to be reviewed once more, especially in terms of defining the design limit states. One area where we are completely at bay is the game of experimental evidence. Today, when we look at experimental facilities across the country, I would doubt that if we have strain controlled facilities for testing basic materials like M120 or M100 concrete or M80 concrete in more than 10 facilities across the country if you leave the manufacturers. And likewise, in terms of steel bars, UTMs, do we have strain controlled UTMs to test a 32 mm bar or 36 mm bar, or in some cases 25 mm bar? It's very few facilities across the country, and hence the data that is coming out of the formal work houses, the R&D houses, is insufficient to come up with a very formal standard on the first cut immediately in the 5th revision. So what's the mandate with this motivation? What is the mandate that the BIS has given us? BIS has formed 3 working groups. Working group 2 is on materials, workmanship, inspection and testing, service life, design for durability and fire resistance, and special concretes. Mr. Arora, V Arora, Deputy Director, NCCBM Ballabgarh, is the convener, and he has a set of colleagues from across the country to be members with him. The working group 3 is on general design considerations, characteristic and design values, partial safety factors, structural analysis, structural design, special design requirements, structural members and systems, and seismic design. This part, I am helping the BIS convene this working group. And we have a very strong group of Arora Saab, Tandon Saab, Rupen Goswami, Mittal Saab, Deepti Ranjan Saab from Delhi, Aman from Delhi, and Rajan Srivastava from here. Working group 4 is on Prestressing concrete. Mahesh Tandon Saab is steering it, and Mr. Vishwanathan, Amandeep Garg, BR Sahu, they are all assisting him in trying to come up with the revised provisions. I must mention here that S. Arun Kumar, Scientist BIS New Delhi, is the member secretary of all the 3 working groups, and he is working very hard to push all of us to get this on the rails and on time. So, me to the matter, what's the scope of the revision? mentioned, we're going to call this as the structural concrete code and not plain and reinforced concrete, because this time pre-stressed concrete is getting added alongside with plain and reinforced, and all the three together will form the new concrete code, and the name proposed is structural concrete code. Earlier we had thought of unified concrete code, but it will become unified if we can get precast concrete, which is not yet on the agenda. Maybe the next revisions we will look at to see if we can bring precast also inside this one. So in all, fifth revision of 456 and third revision of 1343 will together become 456, and we will not have 1343 in the time ahead after this revision is effective. So what do we have in the, what are we expecting in the new revision? We're looking at 11 chapters. Other than the first three, we're looking at basis of design, design loads, structural materials, structural analysis, structural design and detailing, construction, inspection and testing, and dismantling and demolition. This is the overall layout. So as you can see, Mr. Arora's group is working on chapter 6, chapter 9, 10, and 11. Also in chapter 8 in structural design, there are two sections, one on durability and one on fire resistance that he will be working on along with his colleagues. He will present that to us after I finish. He is coming on and is sharing what they are doing, what they have done so far. Let's look at the design loads. These design loads existed in the document at different parts. So now we have collated them into two sets. We call them force loads and displacement loads, right? Force loads, as you are aware, are the traditional loads. We are looking at the typical undergraduate student who wants forces given to him or her through the standard. He or she applies it on the structure, does structural analysis with a fixed base, and then gets the results of bending moment shear forces. So that's the force load part. But what is not taught in undergraduate education largely is temperature load. How do we bring the temperature variation as a matter of structural analysis? Creep load, shrinkage load, elastic shortening, foundation settlement may have been discussed in undergraduate, but structural analysis computer programs don't necessarily all of them have the foundation settlement part. So when you're buying computer programs, you now have to watch out if they can do all these 6 items: earthquake shaking, foundation settlement, elastic shortening, shrinkage, creep, and temperature. So that will be a litmus test for you to buy a computer program. If you can demonstrate all these 6, then you can buy the computer program, because the previous 10 are very easy to do on the computer, because this is the traditional computer analysis. But the new computer analysis has to handle these aspects, which are displacement loads. So that means you're applying displacements or strains on the structure and not forces on the structure. Forces are induced in the structure. So basis of design, I think this is where the first major blow will come in terms of a new look. Basis of design, we now have 6 bases for design: safety, serviceability, durability, integrity, robustness, and restorability. We're using the word limit state. That means we are going to tell you that these are the items when these items are reaching their limiting values. So for these critical items, we give you limiting values, and when these items reach limiting values, then you say that the corresponding situation of the structure is the structure that we are admitting for design purposes. So limit state of safety, so limit state of serviceability, durability, integrity, robustness, and restorability. Now, what are these 6 items? Let's go one by one. Safety, I don't have to tell you. You apply loads and it can't take the loads, right? And that's the game of safety. So what are we looking at? We're looking at strains going past the material limits or strengths going past the section strengths. And I'll elaborate that a little later again. Serviceability, you're familiar. We have deformations in the members, individual members, whether these deformations are acceptable or not. Also, if you're looking at a structure that should not crack, then we need to limit the stresses to less than the tensile strength values in case of reinforced concrete. And crack width should be limited, rotation should be limited, vibration should be limited. All these items will come under serviceability. Durability, you are seeing durability all around you, so I don't have to describe durability. Whether this structure will last is the question. So we don't have so far any method, but now we will tell you that you can design a structure for 50 years, 60 years, 70, 100, maybe 120 years. You can decide, but the responsibility lies on you in ingeniously choosing cement grade, cover, pre-stressing steel grades, pre-stressing and reinforcing steel covers, grouts that you're using, water cement ratio that you will have. A number of list of items are there for checking durability, but you will now be responsible for choosing consciously the life of the structure and put one number on top of the drawing that this is the one that I'm guaranteeing, and put your signature and put a seal under it saying this is my proposal. Good for construction and good for survival for so many years. That is what we will do as practicing engineers in time ahead. Robustness is your fourth limit state. Robustness is to do with blasting, is to do with fire, and is to do with impact. So we are looking at strength, not the design strength, but the inelastic strength, the plastic deflection, the plastic rotation. These will be the items in focus for us in terms of robustness. So now you already can see that we're not talking linear behavior. We're talking on nonlinear behavior already in robustness. Integrity. If one member goes wrong somewhere in a structure, will the whole structure come down? Analysis. And so you're talking about blast, impact, fire, and earthquake causing this one member to vanish. And if that happens, does the structure have enough redundancy? And does the structure have enough inelastic deformability for you to be able to say that my structure is having the required integrity? And finally, very interesting will be the sixth component that we are placing, that is restorability. We have structures that are standing, and I would think about 70% of us will be worried about these structures here and after. So we are looking at assessing the existing structures and strengthening the existing structures as a major focus item for these existing concrete structures. So in case it is damaged or in case it is deteriorated, can we restore it back? But for this standard, the focus is, can you design a new structure to limit damage to accessible locations? That means you as a designer will choose exactly where damage should be and place the damage, allow the damage to occur only there. And those locations should be accessible so that after the incident, we can go and fix that particular portion of the member. Also, the retrofit should not be extensive. That means vacate the whole building, move everybody out, leave me for 2 years. I will decide what to do and give you the building after that. But before that, you give me a big check. No, that's not the method. It should be limited amount of retrofit, and it should be at affordable levels, affordable, commensurate with the structure that we are discussing. Chota structures, middle-rise structures, high-rise structures, kya ho sakta hai? This is what we want to come up with at the beginning itself. So restorability will also find center space, even though you may see that there'll be only a few pages written this time, but we assure you, as we learn more, those few pages will become large number of pages. As more of you will contribute to what is restorability, we will be able to then come up with more clauses, more formal statements related to how to ensure that damage is limited to accessible locations and that the retrofit is actually of affordable levels also. So putting all of these 6 in perspective, you are familiar with where is serviceability and where is safety. This is what you're doing normally, and you're using linear analysis. The graph also shows you that more or less theek hai, linear kar lenge, ho jayega. But this is what you would do in design. But when it comes to robustness, integrity, and restorability, the game is on the horizontal part of the load deformation curve of the structure. So that's where you'll have to change your tools. So linear analysis will not suffice, and you will have to walk into the direction of nonlinear analysis. I must mention here that the younger colleagues did not worry too much. Any point on this graph is also your age. So as you get senior, you'll go towards the right. The younger colleagues can start with linear analysis. Don't get unnecessarily perturbed. Don't try to jump and do the right side items first and then not know the first left side 2 items. Please walk on this line gradually, and over time, everyone will get a chance. There are so many structures in India that all of us have so much work to do. So So you will be able to enjoy doing your profession, provided in the ladder you have put your legs on the first 2 steps. If you have already put your leg on the 5th step, your pant is already torn. So that is not good for us. Please go slowly and climb easily on the load deformation curve along with life and your tools, knowledge, competence, and wisdom. So the one more item I forgot, durability is like Krishna, he's everywhere. So starting from serviceability to safety to robustness to integrity to restorability, durability is always in the back of our head. It's like a halo behind our head. Durability is your key focus. Don't lose sight of that. Every decision of yours has to be conscious about the fact that the structure has to last all through, at least the promised number of years. So remember this big picture. This is what will guide you through the new standard. You should know what tools and what levels are we discussing in terms of rigor, in terms of inputs, in terms of strategies, and so on. So you might say, okay, you've given me 6. Should I do all 6 for all structures? No. We are thinking of saying that the first 3, safety, serviceability, durability, are mandatory for all structures. And robustness, integrity, and restorability are only for optional structures. You can call them special structures. It's to be decided by the owner. So as an owner, I can say, no, I have the threat. I'm doing very wrong things and bombs will be there or trucks will come and hit my building. If I do all that, then I, of course, will have to do robustness, integrity, and restorability also. So I would say that bottom 3 are going to sit on top of the owner as a responsibility to write in the design basis report, this is what I want. But in all structures, the top 3 are non-negotiable, and that is what we showed you at the beginning: safety, functionality, and sustainability. Top 3 are non-negotiable. Bottom 3 are the ones that depend on the seriousness of the structure, importance of the structure, criticality of the structure, and so on. We have some nationally important structures. We have to protect them, come what may. That will come under the total basket of 6 limit states. So let's look at some of the major changes that are coming up. First of all, systems. Now, I won't tell you which are the systems which are admitted, but definitely I'll tell you which are the systems that are worrying us. We are not sleeping in the nights these days because we don't know what is happening with this building that I'm going, the hotel I'm living in is actually on flat slab with pre-tension PT slabs, or it doesn't have any structural walls. What is the lateral deflection? It's very, very worrying to go to any hotel in the country. So we are now saying, please exercise extreme caution when you're looking at pre-tensioning, post-tensioning slabs used anywhere in any system, because in all 100 to 120 mm, 4 major activities are happening: top cover, half of the anchorage, the draping, and the bottom cover. It's a magic that is happening, but I would like to see that the magic is removed and people know exactly the realities. So let's work a little harder and come up with the real truth on these matters. Many of you have seen damages. Many of you have seen distressed conditions. So I don't have to say more, but I'm extremely and deeply concerned, so is the committee, that we don't know how to write sentences to stop this kind of unregulated practice to happen. On the box office are also 5 other hit list items, which is open structures, open story structures, flat slabs used without protection of structural walls, precast systems, pre-engineered buildings, and all-wall buildings. We'll try and admit a few of them this time in, like all-wall buildings and open ground story or open story buildings. But we personally think that we have a long way to go in terms of fixing the middle 3. So we need to learn a little more, lot more experiments have to be done before we can make an emphatic statement. But till such time, it will be best for you not to adopt these systems unless you have evidence of experimental nature guaranteeing that on a full-scale test you have done and you have shaken it and shown that this is in order. Structural walls will start drawing prominence here in time ahead. And one of the major considerations that the committee is going through is that if you're calling it structural wall, it cannot have anything other than 2 curtains of reinforcement and a core concrete inside it. If you don't have core concrete inside, it's not defined as a structural wall. If you have a single curtain and 100 mm it's not defined as a structural wall anymore. That is what we're seeing as a major push, because if you look at even a small shaking back and forth and the cover comes out on either side, only the grill is remaining. And I personally think that the grill may not be able to carry the load of the building that is standing above. So we may have to tighten our belts in terms of understanding that the reinforced concrete means concrete has to be present and concrete cannot be absent. So the larger is the section, the lesser will be the cover area. But if you keep very small section and also single curtain, there is no core concrete. So the limit state method is seeing a small change, but it has a great impact. So we're not changing the basic framework that we had so far, which is strain limit states for axial force and bending moment, and also the combination of P&M, and strength limit states for force and shear force and torsional moment. This is still remaining the same, but the way we are doing strain limit state for bending is going to change. I must also tell you that in the 5th revision, we will continue with the strategy of the 4th revision, but we are poised to now look at a possible 6th revision in which shear and torsion also should go into strain control and not in terms of strength control. This will require a few experiments to be done, and if that is done, we'll be able to win the entire framework of limit state design a lot more respectfully than what we are doing right now in terms of just knowing only the strength of shear and torsion. Because when you do, let us say in the limit state of restorability, you have to do some pushover analysis, then shear, there's no load deformation curve for shear right now. We are adopting some curves that are given internationally, but we have to develop that for our own Indian conditions. Now, the earlier strategy was that we were looking at the strength of a flexural member based on crushing core, crushing of the concrete, core concrete, not cover, but core concrete. But now we are looking at yielding of the steel bar as the basis. That is going to happen much earlier. And we are going to say that we want to have only under reinforced sections. We cannot admit over reinforced sections. That's a major change. We are insisting or feeling that it's very crucial for this nation to have under reinforced sections than over reinforced sections. You might get embarrassed by seeing some of the changes in the geometries that you'll get. If you make this one small change, it will affect your sizing, but don't get too worried. 1960s, the structures were built following this principle only. Somewhere down the line, we economized so much that we lost safety. Now we'll bring back 1960s again. Raj Kapoor's films will become very popular again. Shammi Kapoor and all those friends, Devanand, Dilip Kumar, Rajendra Kumar will come back. Along with all the ladies. I'm not mentioning the ladies because that's too big a list for me. Boys, at least I have only 4 or 5. Now, so the limiting strains, ultimate strain in concrete on the top, and the proof strain, 0.2% proof strain at the bottom. But necessarily we require to control with the bottom and not with the top. That is what is the strategy this time. Just to tell you that the current method is actually overestimating the strength of the walls. If you go by the current method, I'm not worried so much about overestimating walls, but it's actually, if you really want to get that strength, your bar has to elongate 6%. And that is not doable for a structural wall. And that is where our worry is. And that is why we needed to bring back some sanity into limiting the moment. And so from now on, we'll use the word limiting moment and not ultimate moment. We're not going to the ultimate point. We're going to a limit state where the steel is reaching its limiting strain first and not concrete. And that is the point that we would want to use as a basis for design. So you can see here, if you do that with the steel bar, you'll keep it at 1% elongation. But if you go with concrete crushing, you will require the bars to go along with it for about 6%. That's too long, too much. Working stress method. In the middle, there was this excitement that we're going to get rid of working stress method and we'll have all pure limit state design. As Jay Bhadri will say in Kabhi Khushi Kabhi Gum, Galat. That's not true. We just can't do away with the roles and responsibilities of different methods. Working stress method is very easy for us to do limit state of serviceability. Now, some of you can stand up and say, no, I'll use the nonlinear stress strain curve, use limit state method and do that limit state of serviceability. By all means, you can do, but the equations are intricate and involved, and so it will require more effort from your side. The same solution can be obtained easily by the working stress method. As before, both of these methods are tuned, so they will give about the same result for limit state of serviceability. Result in terms of section or amount of steel and so on. So it can't be too different. Results will be about the same. So you will see that for deflection, crack width, all these, the limit state method, which is assuming linear relationship between stress and strain, all that will come in very handy. Materials is an important section. Arora Saab will elaborate in detail. Let me just tell you quickly what's happening. We're looking at major changes in ingredients. Guidance on the use of different cements will come. OPC, PPC, as general purpose cements. Can we use them for normal use? That's the question. Curing water, there's special requirements coming up now. You just can't use any curing water. Chemical and mineral admixtures. These will have to be will be elaborated in greater detail. More types are coming in terms of chemical admixtures, and there will be a limit on the mineral admixtures because new experience has been gained, especially on fly ash and GGBFS for use in reinforced concrete. Materials, high strength concretes are coming in. The new properties that you'll see are stress strain curves, elastic modulus, flexural strength, split tensile strength, creep and shrinkage will come in for these new materials from the test that Arora Saab has done in his laboratory at NCCBM with his colleagues. Also, little other tests that are available from the other laboratories in the country. Grout in pre-stressing has drawn a lot of attention in the recent times. We are pushing any material as grout, not acceptable. Grout has to be the highest, respected item in a pre-stressed member, in a bonded member. And so we will now give you clear guidance on what will be the grout. Now, quickly, just to tell you that how is design life coming in, you have to choose, start with the probability of corrosion initiation. Choose your cover, go to the binder, come up with the chlorination, rate of chlorination, whichever grade that you are in, and then you'll be able to pick the corrosion-free design life of your structure. So this will tell you how to get the quantitative numbers. So that's what I was saying, that you will now fix design life depending on which binder you choose, depending on what is the level of chlorination, with respect to the environment that it is exposed to, and in the design, how much cover have you chosen? All these will determine what will be the design life of your structure. If you want higher design life, you have to have very stringent conditions for the choice of materials, for the cover, as well as in terms of the environment that you have. So service life, as I said, can go up to 120 years. Exposure to different classes, you will see different deterioration mechanisms are there. We'll give you for the basic ones this time, and pray that we will keep adding the new mechanisms in time ahead. Also, now you'll see a climate zone map of India, and the durability requirements will be specified for zone wise. So that will get easier, like you do in seismic zone or wind zone. You will see that it's easy for you for each zone what you have to do. Only thing you have to keep an eye on wind zones, seismic zones, now durability zones also. You'll have to climate zones also. You have to watch out a multi-faceted design that you will do in time ahead. And what is the impact of quality control? Quantitatively, that is what we want to bring about. Let's see what clauses we can carve out for you in this. Procedure is given for carbonation and chloride ingress this time will be given, but in time ahead, we may add more of them. But for the other deterioration mechanisms, deemed to satisfy requirements will be provided this time, so that we don't say that you are open to do anything, but you want to know. Follow this until such time you have more knowledge, right? It's like your mother telling you after finishing school, come back straight with the rickshawala, don't go here, there, anywhere. That is exactly what we're doing. After you finish carbonation and chloride ingress, you just do these and come back to say that your design is deemed to satisfy. That's all. Requirements for protection against sulfate attack and alkali reactions, these are modified. And what is added is freezing and thawing. We are going to have some extra clauses on freezing and thawing. So you can expect some great elaboration in the chapter 6 on materials, and 82, 83, 84 on 85 on durability, and also on fire resistance. On pre-stressed concrete, we are looking at the assessment of the strength of pre-stressed concrete. There's a table that's given, table 11, and you have to choose X by D from there. We are now giving the whole responsibility to the designer to apply equilibrium, compatibility, and constitutive law, and then get one's own X by D. You just don't have to be preempted by the standard to say what will be the X by D. You will, for the steel that you are providing, you can come up with your own exact X by D and not be given any of these prescriptive values. This will be valid for both bonded tendons as well as for unbonded tendons. In both cases, you'll be able to do that. You'll see some interesting ways of trying to estimate these strengths. For this, it will be very, very much in line with what you do for reinforced concrete. So it's not going to be a difficult surprise or difficult item for you. What you do for RC, you'll do for PSC also. Small changes, that's expected anyway. Structural analysis will be greatly elaborated, greatly clarified. As I mentioned to you last time when I showed you this slide, that we have serviceability and safety done with linear analysis, and all others will do nonlinear. So linear analysis is already there, you know it. What you need to know is nonlinear analysis. And in nonlinear, if you can't do full nonlinear, approximate analysis, one level approximation for geometric nonlinearity alone is admitted. For material nonlinearity, no approximations. You have to go through the hard route of doing it full. So I pray that you will quickly learn the nonlinear tools so that you can start using them comfortably for these other three limit states: robustness, integrity, and restorability. I'll have to come almost to the end now. I'm saying that this revision was particularly motivated to increase the sensitivity of is to keep in mind the teachers and see if they can make it enjoyable to learn reinforced concrete design in the classroom and consistently give the same rendition so that students don't get mixed up. For example, last time we said under reinforced, over reinforced, but when we are calculating strength, concrete was always crushing on the top. Now that confused the students. They don't know what to do with that. So that kind of confusions are removed this time. And we are praying that the three documents, SP16, SP24, SP34, come back in a new avatar to our activities. So education is definitely a focus for us. So we are writing commentary and for each clause. So we will pray that the commentary will be a clause and a line, and below that commentary is what we are preparing right now. Indian Standards has to now take a decision on whether to print the two together or print the commentary separately in code separately. That discussion we'll still have with them. I pray that they'll help us make a single document so that we don't have to have two documents and run around hunting for the clauses and pages. So capacity building will get easier, teaching will get easier. The outcomes of the revisions, I said, are 5. The standard itself, then we have the commentary, the design aids, the solved examples. Of course, we are not writing a textbook, but we pray that our teachers in the country who are comfortable with reinforced concrete will start writing the textbooks once the code and commentary are released. So we are looking at currently about 888 pages already drafted, and we're going to add more. I pray that we'll finish somewhere past 1,000 or 1,200, not clear. But yes, it will be an elaborate document. For reading that, you need to spend some time. I pray that you will take a sabbatical for 1 week and read all 1,000 pages and then go back to your regular activity. 1 week you can give for the rest of the 30 years or 20 years or 15 years that you have in your career. So I'll stop here by simply saying that the new look that we are having for the structural concrete code has 456 and 1343 combined. The new limit states are defined, and the focus is on new structures as well as on assessment of existing structures. So design of the new and assessing the old. Both are in focus, and that's why we brought in restorability also in focus and brought in nonlinear tools in focus, because a large number of us will have to do assessment of existing structures. The higher grades of materials that are coming in, is warranting us to change our design calculations. But since we don't have enough experimental evidence in all cases, we may have for materials, but we don't have for member behavior. The combinations of which grade of concrete, which grade of steel is acceptable, that answer we don't have yet because we haven't done experiments yet. So we will have prescriptive statements for the time being, and I pray that you will admit that prescriptive statement as the way of life until such time more experiments are done. I encourage each one of you to encourage the testing houses, the academic institutes, R&D laboratories to do more formal work in the subject of behavior of reinforced concrete structures. I prefer full scale, and otherwise it will be not giving us a complete knowledge of what we have. But we have created, we are creating this document with a lot of love and affection. We want to bring clarity to the users. We want to make it designer friendly, and we want to make it programmer friendly. Some of us are very nifty at putting equations in. So if I give you a table versus an equation, you will put equation there. But if I am a grandfather clause of the engineer's bill, and under that clause, then I'll always go for the table, look for the number, because I want to get physical feel of the numbers. So for some of us who want to get physical feel, we'll have tables. For some of us who are still blind about numbers, there are equations, but somebody will catch you on the numbers. So the success of this new standard will depend on how we understand and implement the intent of the clauses, how well we bring out gaps and shortcomings for future revisions, and how well we provide directions for the drafting group to prepare the new standards. So I invite each one of you to look at the existing documents, look at your experience, and tell us exactly what would be fair proposal. Don't worry about your project that you're doing today. Think of the good of the nation and tell us what is a fair proposal for an Indian Concrete Code, which we can put in this 5th revision of IS 456, which includes. So while I'm saying this concrete, I must mention here that prestressed concrete is not having a separate chapter, but it's going across all pages. So you won't see one chapter for prestressed concrete. You will see only a spread across the document. I'm very humbled to see that this approach of public consultations is being taken very positively by the professional societies. And I would encourage other societies also to take this approach of participating in the development of standards so that the final document that's come in blends smoothly into practice rather than a sudden shock and we have to do large amount of capacity building or training of practicing engineers and architects. We need to support, advise, assist, guide, and help the working group in building this document, but also share with each other all the knowledge, wisdom, and experience that you have. Timelines, you will ask me. We started in 2009. We're praying that if all goes well, if Corona wasn't there, we would have finished the draft by now, but we are pushing it to July. That we'll get a 0 draft in. We will do a lot of discussion amongst the committees in the BIS, and if all of us work very hard and only on this document, we'll finish it by September. And then we put on wide circulation, then all of you will give inputs quickly, and we'll incorporate the inputs quickly. Then we will be able to implement it by January 2021. So this is the most optimistic number. The harder you work, the harder I work, the harder all the work, this number can come true. If this any one of the slips, this number will slide. I don't want this number to slide because it's already 43 years, 42 years, 78% of population. I don't want to see 80% of population getting younger than the age of the standard. So let's get this going at the earliest. And watching only the code committee members running around doing things, I would say that let the code committee members sit up and all of you come into the playing arena. That would be a better excitement for me. Is a small stretch your career longer. It will be 50 years. In 50 years, you can achieve a very great deal but please put it on a ramp, not on a ladder. Okay, the structural concrete code is only on its positive trend now. You just can't afford to slip it. It can't go in the backward direction. So give us only considered opinion that is good for the nation, and we'll take it forward. And this time we'll guarantee you that safety will be on the driving seat. I would thank Alpa Shetji for putting together this forum as membership. A large number of you have come in today to listen to the future of the nation on reinforced concrete structures. And I thank each one of you joining us, but I will thank you profusely in the evening if you give us more inputs that the code committee can work on and build a much stronger code for the safety of everybody. And next time I go to any hotel, I won't feel uncomfortable that I don't know which structural system I'm sleeping under. Right? So let's move from darkness, from untruth to truth, from darkness to light, and from life to eternity. And we'll take your questions through the question answer slot, and we'll answer them sequentially in the post-lunch session. Jai Hind.
Okay, thank you so much, Professor Murty. It was just amazing. I think I was just overwhelmed with the quality of slides, but also as a practicing engineer, I just felt that I was suddenly hit with a brick on my head. And
sorry about that. Actually, this is what happens if after 42 years you come back to try to do something, it will look very different. But if you do every 3 years, it will get a modest, small increment, and that is sustainable. So my prayer is that we don't take this model of 42 years and go with the model of 3 years and then keep revising after 3 years.
Yes, yes. So I think that the entire community of structural engineers will have a lot to share with you in terms of comments and feedback, and I really appreciate that you not only kept to time, but you also gave us some more food for thought beyond what was there in the slides. I do think that it's going to take us weeks on end to actually absorb and digest what you have said. So while we thank you presently for giving us this wonderful talk, we are also going to warn you that we're going to call you back again to answer a tsunami of questions which we will have. So everybody, thank you very much.
Sure. It will be a pleasure.
Sure. Thanks very much.
Thank you.
Thanks so much.
Thank you.
I just felt that we may, since we've actually completed this first session exactly on time, we will have a 25-minute break and we will resume at 11:20. See you then. Bye.
Sure. Thank you. Okay, how do I do that?
Hi everybody. Welcome back. I hope you've had a good cup of tea and you're all ready for the next session. We have a very distinguished guest here with us, Mr. Arora. He is a researcher in the true sense of the word, and he is the Joint Director of NCCPM. And he is a convener for a lot of BIS code committees. He's a member of a lot of those committees. And he is today going to be talking on materials and design for durability. So over to you, Mr. Arora. Thank you.
Okay, thank you, Alpaji. Can all hear me?
Yes, we can hear you. Thank you.
Okay. So I will share my screen and then start. Good morning to all of you. I will be discussing on the topics of materials and design for durability. As Prof Murty had been telling in the morning, this is not yet a finished exercise. We are still working on it. And at this stage, whatever has been kind of agreed in the working group, though some more discussions are also going on, I'm sharing with you for the comments. There is not as much new thing in materials as in the durability part. And we have revised this document based on the research in India at NCB, at IIT Delhi, IIT Madras, and some expert literature referred on these issues. So starting with materials, earlier we had material workmanship inspection and testing, and now we are having a separate chapter on materials which will include prestressing materials also. And then separate chapter on the durability design, or durability you can say, we'll talk about durability in that chapter. Then construction and quality control will be a separate chapter, and inspection, testing and monitoring of structures is a separate chapter. Major changes have been just highlighted by Professor Murty also. Guidance on different types of cements, water requirements updated, more type of chemical admixtures, limit on use of mineral admixtures, prestressing materials and grout of prestressing given. Concrete up to M100 included. Properties of concrete modified in view of the introduction of high strength concrete and new research during the period. Same as for 383. So there have been expanding of weight of different type of aggregates, what will be called as normal weight aggregates, what will be called heavy weight aggregates, and manufactured aggregates, iron slag, copper slag, bottom permitted. Earlier it was mentioned only in 383. So this is now being brought in 456 also. For using lightweight as structural concrete, we have got one document which is sintered fly ash aggregates, which was for structural use. But that we are not directly putting in the main chapter of materials. We are simply referring it, and for using these aggregates, expert literature need to be referred, we have mentioned. And there will be a separate chapter on special concretes, where we will cover this. And those special concretes, we are not covering design procedure in detail in the code. So those are just to be a touching like fiber reinforced concrete and lightweight concrete, so that people, we give some guidance in that, and then more literature can be referred while using those special concretes. Similarly, here also. Cements, earlier we had been listing all cements in one go, that all these cements can be used. And whenever you interview a student, engineering student, okay, what are the common cements, he will start from rapid hardening. Most of the interviews, we had been seeing that. So students won't know what is general purpose cement, what are special purpose cements, specific cements. So now this is separated out. OPC, PPC, PSC, they have been put as general purpose cements. And other cements have been listed, and some guidance given on that, at where those specific cements are used. Like composite cement, the new code has come. It was not in IS 456. But as of now, the present of the composite cement is such that we are not permitting it for RCC as of now till the code is revised to some extent. So composite cement is permitted in the plain concrete, which is not containing reinforcement. Microfine cement, this is generally used for rock grouting and all that. Super sulfated cement, SRPC. So these are sulfate resisting cement and special application cements. So there, these are to be used. What are the applications that have been listed in the code? Coming to the water. Some more details have been added. What kind of water can be used? Natural surface water can be used. Treated water can be used. Water recovered from process in different concrete industry that can also be used. Water from underground structures, recycled water, desalinated water. But all these waters also, when we are using, they have to comply to the requirements given in the table. Seawater we are not permitting as of now. These are the limits where we have not made any much change here. So any water complying to these requirements and some additional requirements we have added now, which I will come to that. Only thing is what we are saying here is like we are permitting chlorides up to 500 in RCC, and ISO up to the 1000 is permitted. So what we are saying is this was earlier from 1000, which was brought down to 500 later on, because the chloride limit in cements were increased. But many of the cements have got low chlorides. So what we are saying is if the total chlorides are within limits and it is tested specifically for the hardened concrete also, then up to 1000 milligram per liter may be permitted. For curing water also, we are not changing much of the specification, but for example, chlorides up to 1000 milligram per liter. This is commonly used in many of the countries even for RCC. So this much we are permitting in curing water. Because for curing water, then when we say 500, then people don't have, and then without telling, people use it also. So we are giving some liberty, but if it is more than that, then they have to use the different water. Sulfates and chlorides, some minor changes have been made here for the curing water. Sampling frequency of water has been added, it was not there earlier. So that it is water quality keeps on changing. You know, people source keeps on changing. If some people are using tanker water many times, so then it is changing quite a bit. So it has been mentioned that it should be tested every 3 months, and if it is no change in fluctuation, then we may the engineer in charge may allow the longer frequency. Coming to mineral admixtures, all these admixtures are already permitted: fly ash, silica fume, rice husk ash, metacholine, ground GGBS. So now ultrafine GGBS has also come, and that also we are permitting use in concrete. Other major changes with respect to mineral admixtures in proposed IS 456 are the total replacement by fly ash and silica fume shall not be more than 35% for reinforced cement concrete. What happens is when we put fly ash in concrete, the carbonation increases at a faster rate, and which affects the durability. So there has to be some limit. 35 we have put because PPC is permitting 35 as of now, so we have put 35. I would have preferred rather 30, but this is as of now agreed 35. Similarly, total replacement by slag and silica fume shall not be more than 60%. This is for mixing at site, not in the cement as such. These limits shall also apply when PPC or PSC is used, because even if you're using PSC and then you cannot put additional silica fume if the slag already there is 60% or more is there in PSC, then you cannot use additional silica fume because that also increases further carbonation. The limit of PSC of 70% is actually too high. That also need to be revised in due course. For concrete having steel replacement level of GGBS shall be restricted to 50%. It should be 50% when used alone GGBS that side as replacement of cement. Water demand and drying shrinkage should be studied before using rice husk, including performance and uniformity, since rice husk can have deleterious material as silt when incorporated in concrete. Rice husk has got more variability in the quality, so these precautions have specifically been mentioned to be taken when you're using rice husk. Chemical admixtures, though chemical admixtures will be covered only in 9103 in detail, but we have mentioned in 456 that these admixtures can be used when conforming to 9103, but 9103 doesn't have these admixtures as of now. So we are parallelly revising the 9103 also to include these chemical admixtures. where we intend to use shrinkage reducing admixtures because they are being commonly used in the country. People are using it. Corrosion inhibiting admixtures, permeability reducing admixtures, non-hydrostatic type, and permeability reducing admixtures, hydrostatic conditions, PRA and PRAN they are called. Shrinkage compensating admixtures shall not be used in the country. This we are not permitting. Shrinkage compensating is the admixtures which they cause expansion to some extent to cover up the shrinkage. So they are not reducing the shrinkage, they are doing some expansion. So if expansion is little more than the shrinkage, it can cause be disastrous. So this is not permitted in structural concrete. Grades, earlier also we had 3 categories: ordinary, standard, and high strength concrete. So this we 3 categories we are maintaining, but we're going up to M100 now. Ordinary concrete is M10 to 20. Standard concrete is 25 to 60, and high strength concrete is 65 to 100. No, it is not. Earlier, this definitions were not there, so we are defining this nominal mix or design. Ordinary concrete can either be nominal mix or design mix. Proportion by weight of ingredients. All proportioning will be by weight. It may or may not contain chemical admixtures. In up to M20, you may not use chemical admixtures, but beyond 25 and above, we recommend use of chemical admixtures. It has to be design mix. Any standard concrete when we specify. So there has to be a design mix, proportion by weight, and it contains chemical admixtures to achieve certain target values. In fresh concrete, achievement of which is monitored and controlled during production and suitable tests. High strength concrete is similar to standard concrete, but it contains additional 1 or more mineral admixtures, providing binding characteristics and partly acting as inert filler, which increases the strength and reduces the porosity and modified properties in terms of fresh and hardened concrete. This was the concrete making materials we had been talking. Now coming to concrete as a material. So materials covers both. It covers the ingredients as a material and concrete properties also as a material. So both are covered in the material chapter. Properties of concrete. Properties of concrete which are as a material effect are the which is to be taken in design is modulus of elasticity. So this equation is modified 10,000 FCK power 0.3. This is somewhat similar to Eurocode, where FCK is the characteristic strength. But this E value is the value to be taken in design of RCC structures. This is what they are. For now, and this is for the quartzite aggregates. The modulus of velocity changes with the type of aggregate also. So for limestone and sandstone aggregate, the value should be reduced by 10% and 30% respectively. For basalt aggregates, the value has to be increased by 20%. So this is a middle case of quartzite, which is commonly available in the country. Basalt is more available in the South India. Poisson ratio for elastic range may normally be taken as assumed to be 0.2. However, it should be taken as 0 when cracking is allowed in tension. For example, if some member has got direct tension, so there the Poisson ratio is not to be considered. Axial strength equation is same, but we have called it a characteristic value, and then mean value can be determined like this. As we determine for the compressive strength, it has to be characteristic plus 1.65 into standard deviation or FC plus 0.55, whichever is higher. Equation for split tensile has been added. It is at FCT split tensile 0.5 into root FCK. And here also the procedure for getting the mean value is indicated for design purposes, design mix stages. Creep has been revised. Creep in 456 was different from what was given in IRC 112 and elsewhere, Eurocode also, FIB, everywhere it is similar. So taking from the similar approach of FIB, which is used in IRC 112 also, this has been modified and however somewhat simplified, and 3 levels of creep have been provided. Creep level 1, creep level 2, creep level 3. Creep level 1 is for RCC beams, frames and slabs spans up to 20 meters and height up to 30 meters. Similarly, creep level 2 is pre-stressed beams or slabs of span up to 20 meters, buildings up to 100 meter height, and cable stayed bridges and all that. And creep strength 3 is further higher. Pre-stressed box girders, cable stayed arch bridges which span more than 80 meters. They are covered in creep. At creep level 1, the coefficient are only for all sizes, single coefficient, like in the existing code have been given with minor changes in the values. Creep level 2, the values are changing with the grades of concretes. 3 slabs are there, M35 to 45, M50 to 65. And for different sizes of members, notional sizes, you can relate to your member to these sizes. And these are the age of loading. So these tables have been given. If you see the 28 days loading stage, there is not much change. For example, this here it is 2.1, 2.48. And when the sizes are bigger, it is somewhat similar. So only thing it is a little more rationalized. In case of higher grades, the creep is less. In case of lower grades, the creep is more. Creep level 3 is when we go beyond 75 years service life. So some notional increase in creep is considered here. And for which formula have been given to increase the creep, which is calculated in the previous level 2 to level 3. Then some additional coefficients have been given. However, these coefficients are applicable when the compressive strength does not exceed 0.36 FCK at the age of loading, and mean temperatures are these ranges, varying from -20 to 40 degrees centigrade. If temperature increases, the creep coefficients have to be multiplied with the coefficient. Shrinkage of concrete, this is generally in line with the 1343 taken and merged with 456, same has been adopted, which depends upon the constituents to some extent, and it is a combination of autogenous shrinkage and the drying shrinkage. Autogenous shrinkage has been given grade-wise, and drying shrinkage has been given for 2 values of relative humidities in the ambient conditions, 50% and 80%. And for different grades of concrete, the values have been given. And a coefficient of to be multiplied is based on the size of member. Stress strain of unconfined concrete. Normally, in the existing code, we had this kind of idealized curve, which was common for all the grades of concrete. We had this 0.002 strain at peak and then ultimate strain at 0.0035. But what happens is when we go for high strength concrete, it is it is more brittle, like you see from these curves. These are for lower grades, and this is for the high grade. If you go to M100, the curve becomes like this, which is more steep. And there's not much difference between the peak and the ultimate, like we have here 0.02 and 0.003. There's a big gap. But here we don't have in this, if you see the top, this is nearly matching. So keeping in view this, or this range of upper side, we have got, this is a lower grade where we have existing values up to for M20, and then we are proportionally increasing it up to 100. And if you approach M100, you will see these both values are matching, 0.024 and 0.024, because here there's no difference in peak and the ultimate. So in case of M100 also, we are taking this, and it is gradually reducing to M20, where we have got the existing values of 0.02 and 0.035. So accordingly, the stress block parameters will change. It will become dynamic depending on the grade of concrete, which will be discussed in detail by Professor Rupen Goswami in his presentation. Just a minute, why it is not moving now? Okay, sorry, it was stuck somewhere. Coming to stress strain curve of the confined concrete. Now we didn't have much data on this confined concrete. The previous curves of different grades. We had a lot of research here done in our country at NCB, at IIT also, based on which we had agreed to those values. But for confined concrete, we are taking these values from the Eurocode mainly, where the strength, depending upon the confinement, the strain values and stress values are modified as per the equations given. Steel reinforcement up to M550 grade permitted, taking into the consideration of 13920 16 provisions. Now, in this code, steel reinforcement up to 600 has been permitted, as was told by Prof Murty also. Now, in this code, we are keeping a upper capping on the yield strength. Minimum value ratio of actual tensile strength to yield strength has been introduced in line with the 13920. Earlier, we had it in 13920, but in 456 we didn't have it. So we have put this actual 0.2% proof stress of steel bars based on tensile stress must not exceed the characteristic value. 0.2% proof by more than 20%. Similarly, the ratio of ultimate to yield shall be at least 1.15 and not more than 1.25. Coming to prestressing steel, it was not there in 456, but now we are merging with 1343. So this is also introduced in that in revised draft prestressing section covering grades, mechanical properties, stress strain characteristics of prestressing steel is now added into materials chapter in line with the 1343 and IRC 112. We had certain things in 112, but we were not having in 1343, so they also have been brought in here. Mechanical couplers have been put in there. Testing method for prestressing tendon grout and specification for PT grout has been introduced. This is based on specifically work done at IIT Madras by Professor Pillai and others. Test on mild steel and corrugated SDP ducts, including general requirements of protection grouts, has been added in this section. Now, this I had put quickly what the changes in this, and now we can discuss the durability part. Now, durability, we have, as morning it was being discussed, that we are given procedures for the design of durability, choosing the cover and the grades to meet the durability requirements. However, because this is a very complex procedure of durability, there are so many factors and every factor cannot be accounted for. So we have taken some simplistic approach because there are lot many factors like type of binder, even within the particular type, what kind of chemistry is there, then the ingredients, mixed design, the SEMs, the environment also, there are so many factors, internal, external. So each factor cannot be put in. So some writers also have to be put in based on the experience. So as we were talking about the design that we are keeping working as well as limit state, here also we are now keeping a limit state approach of durability design for carbonation and chloride. At the same time, we are keeping the deemed to satisfy kind of table also like we had earlier, but with a modified form and for different types of cement. I will discuss that. So that also is kept up to 50 years of service life. Beyond that, we have to do a detailed one. But those are certain minimum values we have to follow it. So what we are covering is exposure classes we have changed, design for durability we have changed. Then we have permitted some protection measures, not much detail given on that. Concept of design for durability has been introduced. Concept of service life introduced. Provision for durability design for 50 to 120 years. Exposure classes for different deterioration mechanisms. Map of India showing climatic zones, including and linked to durability requirements. Like I was saying, we are not to simply put in the individual because humidity matters, the drying and wetting matters, but every individual cannot put his own input parameters, so it is linked to the climatic zones. Effect of quality control levels to be considered while designing the durability. So some factors have been introduced for that. Those factors can be refined anytime, but at least those concepts we have introduced. However, the details of quality levels will come in the different chapter of the quality control. Now, for carbonation and chloride, we are giving detailed procedures and separate deemed to satisfy table given for different detection mechanisms. Requirements for protection against sulfate attack and Alkali-silica activity modified. Requirements for resistance against freezing and thawing have been added. Durability testing also introduced. Because performance, we are making code performance-oriented specifications we are making, like grades or workability. There are already performance-oriented specification. So similarly, for durability also, we have to introduce the performance-based specification. One is perform a design, then perform a specification also when we are using the concrete. So some durability tests are to be introduced. There are many tests like electrical resistivity, RCPT, oxygen permeability, bulk resistivity, air permeability. So based on the data available, we have introduced that. I will discuss on that. This is the existing table. We had moderate, mild, moderate, severe, but we are not talking what kind of a mechanism is there, where the structure is situated and all. Present draft durability exposure environments are based on the chemical and physical conditions to which the concrete structure shall be exposed. Different type of environment conditions are classified. If you see this map of a country, this black dot line at the bottom along the coast, now this is our coastal area. Area close to this coast, mainly 1 kilometer, 2 kilometer area, they are deterioration mechanism is the chloride grass. Chloride. Most grass are being done for the chloride. All durability testing, you see any research paper, people do RCPT test and they say yes. Now, those tests may not be valid for to predict the carbonation. It is affected by the different types of cements also. For example, when you blended cements, carbonation resistance will be reduced, but wherever these tests will show enhanced durability, because that enhanced durability will be against chloride attack, not against the carbonation attack. So this, and I think we have to understand it. What happens is in the, for example, I was saying this area, whole of area, these structures get deteriorated mostly because of the ingress of carbon dioxide and the availability of moisture. So moisture availability and then moisture availability, then cyclic wetting and drying, that also matters. The average humidity also matters. So we have got 4 zones here: hot and dry, warm and humid, composite zones, and one is the cold zone. I will discuss those things. Now, what happens in carbonation? When the we have got reinforcement has got a passive film when we do RCC work. The calcium hydroxide present in the concrete, which is generated on the hydration of the cement, that provides a passive layer on the reinforcement. And when the carbon dioxide goes in, it reacts with the calcium hydroxide and disturbs the passive film, and the corrosion starts. That is the main mechanism in most part of the country. Chloride ingress is only in very small parts of the country. And when the carbon dioxide goes to certain depth, this is the test for carbonation. For testing of carbonation also, we are making a IS 516 part also on that, testing of carbonation. Now, this rate of ingress of carbon dioxide will be determining your service life. And this varies from different types of cements, different type of binders, with different water cement ratios. If it is more dense, it will be slow. If more higher pH value, your carbonation will be lesser. If there is a low pH value already in the system because of blended cements, high value of fly ash, 50% of fly ash, the pH level goes down to anything. So there is hardly any protection available to reinforcement. So if you know the carbonation coefficient, that is what rate the carbonation goes inside, and then we can determine the service life because we know the relationship of that. We have got equations with that. So this is for different, coming to the chloride level, for different threshold values, we can have, for different cements, we will have different cover requirements. Here it is reverse. OPC will perform less and it will require bigger cover, whereas PPC and PSC will perform much better. PPC and PSC are more durable than OPC in coastal environment and grassy environments, owing to high resistance to chloride ion penetration. When we put fly ash or slag, the resistance to chloride ion penetration increases significantly. And OPC is more durable as compared to PPC in case of non-coastal, non-grassy environments, where distress due to carbonation is critical. So these are the exposure classes now which we are making. If it is carbonation-induced corrosion, for different climatic zones, we have got hot and dry, warm and humid, composite, and cold and mountainous. For this map is already given as I'd shown you. From this we can know which area we are there, and then accordingly we can have for different internal members. We can select our exposure class, and chloride induced corrosion, if it is there, it is near C or somewhere. This is chlorides other than from C. It can be from any aggressive environment. CH1 is for wet and rarely dry. CH2 is cyclic and wet and dry. Similarly, corrosion induced by chlorides from seawater. Now here what happens is SW1, SW1A, exposed to airborne salt but not direct contact. That is SW1. Now structures near the coastline within 1 kilometer is 1A. B is structure located 1 to 10 kilometers and 10 to 50 kilometers. Now 10 to 50 kilometers is mentioned here, but generally chloride will not be critical in this zone. So we have put a note that these structures should be checked for carbonation also, and chloride also you have to check it, because the chloride values are low in this case, which are to be considered. That those values have been given in the code. Similarly, sulfate attack, we have given 5 conditions, and freezing and thawing also 3 conditions for which the guidance has been provided. Now coming to the design for durability, this I think mostly we discussed. We come to that. Now coming to the carbonation induced corrosion procedure, sorry. We have provided a design table for normal structures subjected to carbonation for 50 years design service life. For quality control levels of 2 and 3 and importance level of 1. Design table gives requirement of minimum cover, limiting value of maximum water cement ratio, water cementitious ratios, cement content and type of cement, minimum cover requirement, and durability test requirements. This is existing table. We had a very small table and it was not related to this type of cement being used. This is the new table we are giving for 50 years service life, quality control level 2 and 3. What is 2 and 3 will be discussed in the quality control chapter. Now here, for example, the hot and dry environment. For external members, if using OPC, then these are the values of cover, water cement ratios, and minimum cement content you have to maintain. If you're using PPC or OPC with fly ash, then these are the values which you have to use. Similarly, for other conditions, for warm and humid and temperate environment, for internal environment member it's different. For external member, it is stringent. And similarly for composite, where the alternate wetting and drying is there mostly. Internal members, these are the requirements. For external member, these are the requirements. And it is all everywhere we are given separately for different types of cements. And the durability requirements here have been given in the terms of electrical resistivity values, because we had data, significant data on electrical resistivity, which was giving a good correlation with the water cement ratios and the carbonation depths. Other tests can also be used. Even at this stage, we will be permitting that other tests like oxygen permeability, bulk conductivity, bulk resistivity can be used for quality control purposes. For example, you do a mixed stage, you achieve these values of the electrical resistivity, and you do additional tests which you want to use for the quality control purposes. And then how to, what will be the acceptance criteria of those tests, that will cover in the quality control chapter. So you can do oxygen permeability test along with this, and then you can achieve those values in the field. So that can also be permitted. However, we are trying to include oxygen permeability values. We are trying to gather data on that. If we get more data, we will put that also in this. Otherwise, in any case, that can be used for quality control purposes. This is for composite environment cold environment, cold mountainous. C3 was already discussed. Internal members and external members, and then we have put some notes as they were earlier in the also. Now also we have put some notes that where the grade of concrete is more than M30, you may not do the durability testing, may not be that essential. And for quality control level 1, where the durability tests are not being done, minimum grade can be increased. So those kind of additional notes have also been put for adoption at different areas where we don't have facilities, or where we're using a very high quality concrete, then this durability test may not be of any value, because we will be achieving it in any way. Now, that is the kind of a minimum requirements we put in the table, but for the higher values of importance factor or for the longer life than 50 years, we have provided a procedure for the limit state design of carbonation induced corrosion. The basis of following parameters. Now, first we see what is the definition of limit state for carbonation we have to use. Limit state of durability for carbonation induced corrosion will be the initiation of crack due to reinforcement corrosion due to deep excavation caused due to carbonation process. This is how we are defining a limit state. So when you achieve this limit state, so your service life is over. So that is how it goes. This is a presumption for new buildings. It is not existing buildings that for crack has come and service life is over. We are not saying that, but this is a design process for the new structures where we have to say how we design. So that's a systematic procedure which everybody has to adopt. Now, how we when we take a limit state design, we have to have some of the load factors and then the resistance. Now that is how we do a limit state even for structural design also. Similarly here also, we have to consider actions and effects and the resistance to those actions and effects. Actions and effects include the characteristic values of CO2 levels in the environment. For urban environment, CO2 level will be more, in rural environment, CO2 is less. So your structures will last longer because concentration of CO2 matters and the weather coefficient. So these are our load factors, and resistance comes in terms of the carbonation coefficients, and that is which is an indicator of the resistance to carbonation, and the cover to the concrete provided. More is the cover. For the same resistance, same type of concrete, you will have more service life. So that's the more resistance we are giving. So these are how we resist this actions and effects, by providing more cover and providing lesser carbonation coefficients, so which gives more resistance to the carbonation. So lesser the carbonation coefficient, your more is the resistance. And then we have the verification process, like design verifies through the equations that what is the stress generated and what is the stress permitted. So here we first of all we have to verify the carbonate coefficient we are assuming. First we assume the water cement ratio, and then we verify through the durability test which we have shown, electrical resistivity or other tests. From that we will verify that we are achieving these values. Or through the accelerated carbonation test also we can use. That has also been mentioned here, that you can do accelerated carbonation testing, but that test takes around 90 days to 1 month, 100 days of time minimum. Calculate service life for TL to be more than the design service life, that is the limit state. Now this service life of carbonation up to the limit state prescribed consists of two parts, because limit state is initiation of cracking. So first is the initiation of corrosion. So that is the first part, and remaining is the propagation part from initiation of corrosion to the cracking. Now we have got reasonable model and data available on the first part, that from the date of new structures, concrete laid, to the initiation of cracking, we have got more data and equations are available. But for the propagation period, the process is more complex, and though the models are available, they are more complex. And as of now, they have not been included. And for the propagation period, we have given fixed values. So we can deduct from the service life, we can reduce minus the propagation period, and from the equations we determine the other parameters. I will just discuss on that. These are the values of CO2 levels we are taking for different exposure conditions in different areas. For urban buildings, for rural areas it is less, for areas away from urban areas. For urban areas and industrial buildings it is more. External members 450, internal 400. So this is how we are taking it. Then these are the equations based on water cement ratios, from which we can determine based on water cement ratio, we can assess the carbonation coefficient of different concretes, different for OPC, PPC, and PSC. And similarly for different amount of fly ash added in OPC, we can work out the carbonation coefficients. Then we work out the mean value of coefficients by adding some standard deviation, which can have levels also. And then design coefficient to be adopted design, keeping some margin of safety on that, which we are putting one not very high factor of safety, because 1.1 is also changes the structural requirements significantly, cover requirements and grade requirements. Nominal, then we have come to the minimum cover. We have got a nominal cover, then we have design cover. We put some factor of safety, because if your quality control is high, we are keeping it 1, because we are not permitting any negative deviation in the cover in our specification tolerance factor. So, but where the quality control level is poor, so the cover can come down there also. So we are having some factor of safety on that also. So to determine the corrosion initiation period Ti, we have got this equation. From this, we can determine the time to initiate the corrosion, and added to that the propagation period, we get the total time to cracking, and that should be less than the design service life. That should be rather more than this design service life. Now this X value, power value, this depends upon the type of binder. For OPC it is 0.6, for PPC, PSC it changes here also. So based on this, we work out the service life. Propagation period ke liye, now we have table which is based on the grade of concrete, type of exposure class, type of member, type of cement. Now this propagation period, we have kept 5 years to 15 or 13 years for different type of structures and these parameters. And remaining part has to be determined from the equations and the given in the code. Coming to chloride induced corrosion, here also the approach is same. We have got a design table and then the procedure also for the design. Initial chloride, which is already given in 0.6 in the present code, but this had come earlier from 0.15, which earlier also we had put 1.1% by mass of cement. So this we are introducing again. It will be 0.15% by mass of cement or 0.6 kg per cubic meter, whichever is lower. And for hardened concrete, how to determine, we have mentioned separately. Total acid soluble chloride should not exceed 0.2% by mass of cement. And where the cement content is not known, there also the values have been given. And minimum grade of concrete for PCC M20, for RCC M35, where the chlorides ingress is there. Table is given again here also for 50 year service life, which gives minimum cover requirements, limiting values, minimum cover requirement, durability test requirements, similar to the carbonation process. This is the table where the chloride induced corrosion is there. Here also we are given separately for OPC, PPC, PSC. These values are not final as of now, which may change slightly. We are trying to work out more on this and trying to vet it as from various data available. Coming to demonstrate design of chloride induced corrosion. Here also the processes, the actions and effects are surface chloride level, what is to be considered in design, and the threshold value. And resistance is provided by chloride diffusion coefficient here for different binder types and cover of concrete. There we had carbonation coefficient, here we have chloride diffusion coefficient. And verification, again we do verification of the chloride diffusion coefficient and then the verification of performance against chloride and ingress. Now what chloride concentrations we consider for designing? These are the concentrations. Near shoreline we take 9 kg per cubic meter at surface chloride, surface level chloride content, and at 1 kilometer to 10 kilometer it is 1.75 kg per cubic meter, and 10 kilometer to 50 is 1 kg per cubic meter. Now this 1 kg is quite close to 0.6, which we are permitting in any case as an initial chloride in the concrete itself. And at this level generally the corrosion does not occur in many of the cases. So that is why we are saying when we go in this level, we check it for carbonation also. The carbonation may be critical more here than this. And this SW2, and which is the where we have chloride swimming pools and other areas where we have chloride, high chloride, there also 9 kg we have taken. Threshold chloride content, earlier generally in the ACI also it was taken 0.4 by mass percentage by mass of cement. But research done, specifically this data given by Professor Radhakishan Pillai from IIT Madras, they have found that in case of PPC and PSC, though the resistance to chloride ion is more, but here also the threshold value is less than the OPC. in case of OPC, when near the threshold means threshold is when the chloride concentration near the reinforcement. When the chloride concentration near the reinforcement reaches 0.4% by mass of cement, then the corrosion initiates. That is called threshold limit. So in case of OPC, you are taking as 0.4%. In case of PPC, when 0.3% concentration of chloride is there near the reinforcement, then we can say the corrosion will be initiated. So initiation of corrosion. So we have to determine the time from the surface to the reinforcement level it takes to reach these levels. So that is our corrosion initiation period. Now, for this, we are using a model which is based on this law. This model is also may not be actually usable everywhere, but the other models are also available, but those models are complex, and for normal structures it will be difficult to use. So we have put this for general use, and special literature can be referred for better design, but not less than this. Stringent values can be used if you see from other models. Coming back to this, now these are the equations from where we can determine the chloride diffusion coefficient based on the water cement ratios. This is based on the work done at NCB and then validated from the data from other places. So first we determine these values, then we put some factor safeties depending on the quality control levels and the variability. And then doing some regression analysis, we see the whether what is the concentration at X is the cover depth and time. At that time, this is initial surface chloride. So based on that, we try to determine the time taken, T value for different T values. So we determine the time taken to initiate the corrosion from this equation. These functions, error function values are given in Excel also, and we will be attaching a table also in the code for the easy reference. But in case of chloride and gas, one thing is there, but here, but I had mentioned somewhere the definition of the here the definition of limit state of the chloride. We are taking at, like in case of the carbonation attack, we had said when the initiation of crack will be the threshold. Sorry, the limit state. But in case of chloride attack, the limit state is taken as the time by which the threshold value is reached. We don't wait for the crack. So when that threshold level is sorry. So when that threshold value of chloride is reached at the surface of the reinforcement, we consider that as the limit state here, because in case of carbonation, at many places, the propagation time is very long, say 10, 12 years. But in case of the chloride, because moisture is available mostly here, the carbonation time is less. Sorry, the propagation time is less. So that has been ignored, and threshold value has been taken as the limit state. Coming to the sulfate attack, this table has been revised. The exposure class is not much different from the earlier one, but what is happening here is that this is existing table, and this is a new table. This is not yet finalized; it is yet to be discussed, and these values are not yet filled also, and this also. But what we are going to introduce high strength concrete in this. When high sulfates are there, we will go up to M50. Earlier it was only we are going up to 0.4 of the water cement ratio, and that was all what we were saying and then we were saying we provide protective coating. But now we have got high strength concretes available, so we can use M50. Earlier it was not so easily available high strength concrete, but M50 is rather no standard concrete. It's not even a high strength concrete. It is not even a high strength concrete. So we will be introducing this high strength concrete, and then we have to finalize these values. Freezing and thawing has been discussed in the new code. Process, factors affecting, table for mean total air content, design table, recommending use of silica fume. I've not given here the table, but we have given air content values for different levels of the exposure conditions. Like in freezing and thawing also we have made exposure conditions, 3 types, 3 levels of that freezing and thawing. And for different levels, the different air contents have been mentioned. Alkali aggregate reaction process is same: alkali aggregate reactivity, alkali-silica reactivity, and alkali carbon reactivity. This is silica, not aggregate. Test methods: accelerated motor bar test was not there earlier. Now we are introducing this also, accelerated motor bar test. Mostly ASTM motor bar test is used, so similar test. Now we are also making in that, and the motor bar test is already there, so that will follow. In mitigation measures, we had been saying that additional advantage can be used by putting fly ash and use of PPC. But here we are saying now alternatively PPC can be used. It is not that only OPC has to be used and additional advantage will be taken. Because PPC and PSC, they provide a distinct advantage over OPC in case of alkali aggregate reaction. They provide very high resistance to mitigation. And there are test methods to again verify. So what we can do is not only do the standard testing, we can use the proposed PPC and PSC and do a test. And if the expansions are within limits at 16 days, if it is less than 0.1%, so we can use that. So these are some of the changes made in that. It is a kind of updation, nothing, no major change as such. And then some protection measures, like it was mentioned in the sulfate case, but in general it wasn't mentioned. But here we are putting a separate heading on protection measures and methods. Like when we design for durability, there are sometimes if you're designing for 120 years life, service life and all that, and your concentrations are very high, your factor of safety you're taking high, your normal procedure of providing high strength concrete you may not feel adequate. So you can have additional protective coatings also, like applying surface coating using specific products for concrete, paints or coatings, protection of reinforcement using coatings, for example, galvanized reinforcement, cathodic protection of reinforcement, stainless steel reinforcement, and active corrosion inhibitors. Now, we have not given much detail on how to design for using these methods, but they have been introduced, and in due course, as the data, more data and research goes into these, so further specifications can be added on that. But as we start introducing the things in the new course, then research also starts moving, and more data comes in, and we can refine it later on. And we have also put the annexure with this, which gives the determination of mean carbonation coefficient from accelerated carbonation resistance as per 516. Now, these equations which we have been drawn and all that, they are all based on the accelerated carbonation testing which we do in the laboratory at 1% level, 3% level, 4% level. We have gone up to 4% level. But earlier, this test procedure was not there in our code. We were following ISO procedures, ASTM procedures on the battery. Now we have made a 516 part 2 section 4, and wherein this test method has also been given. Now how you can use this test method to determine the carbonation coefficient for use in durability design. So we have put a small annexure in this, because one verification of the carbonation coefficient we have given by doing the durability tests like electrical resistivity test and all that, but those are indirect tests. This carbonation coefficient test, accelerated test, is a more direct test. And similarly, chloride diffusion test also we can use. Chloride diffusion test is in fact takes 4 months. So for bigger projects, you can do that also. So these tests are also now available in our 516. We can use that, and coefficients determined from that can be used in the durability design procedures. Or otherwise, we are giving a quick method where you can use electrical resistivity and determine, okay, and based on the equations, we can determine, that is assessment we are making for the carbonation coefficient and the chloride coefficient. Similarly, electrical resistivity we have mentioned here, but we don't have a test procedure as of now. So till the time we put electrical resistivity also as a separate code in 516, we are putting an annexure in this, how to do that test. So that annexure has also been added in this. So with this and remaining work, we are working in this working group is on the construction quality control, where we will try to introduce the statistical quality control and more detailed acceptance criteria, and which will come to you later on. So with this, I'm closing it now. Thank you very much. I hope I'm in time.
Thank you.
Weird, so I thought it is time, so I closed.
No, thank you so much, Mr. Arora. Thank you so very much. It was fascinating. I must say that you took us into a completely new territory of design for durability. And this is not just exciting, but it is also very timely. And frankly speaking, for the rest of the design engineers, I think we just can't wait to get our hands on the draft when it is ready to really actually get our hands dirty, so to say, in designing for durability. Once again, thank you very much. And dear colleagues, I hope you will forgive me if I would suggest that we kind of skip the next break that we were to have. And instead, we straight go on to the next speaker, which is Professor Rupen Goswami. Just bear with me for a minute. Just a second. Okay. So I think all of you have had a chance to see, as I had mentioned, the two books on earthquake behavior of buildings and earthquake safety of building contents. There's also a very interesting other book on confined masonry, which Professor Rupen Goswami was also involved in co-authoring. So I have seen some really fascinating work which he is even doing in steel in terms of the experiments, and I hope that you get a chance to see more of what he's doing at some point when you read his papers. As of today, he is going to be talking to us about the design details in the proposed new IS 456. Just to give you briefly that he is an associate professor at IIT Madras, and like our two other speakers, he is a member of a lot of the BIS and IRC code committees. So with no further ado, let me just hand over the controls to Professor Goswami. It's all yours.
Thank you so much. Am I audible?
Yes.
Okay, great. Thank you so much for the introduction, and good afternoon, ladies and gentlemen. So in this session, we are going to have a first look at the probable key structural design provisions in the upcoming new revision of IS 456, and of course, this includes the provisions of the Prestressed Concrete Code 1343. Now, 456, IS 456 is a very, sacred document, so to say, very close to every engineer's heart. And therefore, when BIS initiated this task, everyone associated with it knew that it's going to be a difficult one, especially because it is being done after decades. But this challenge brought in opportunities to do something for the country, and so everyone resolved to do the best that is possible. And we are all grateful to BIS for this opportunity. Also, as mentioned, this is a consultation that is being done even before anything is finalized. And for this, I think all of us should gratefully acknowledge and appreciate the effort that is being put in by SEFI and the SHADE in particular for hosting us all together today. So with this, let me move on to the main content of this particular presentation. And as both Arora ji and Prof Murty mentioned, the need essentially arose due to a lot of changes that happened in the materials aspect. We have brought in a lot of new materials, a lot of new construction technologies, and a lot of new structural systems. So it is quite pertinent that we should have a lot of changes to the code, and many revisions should be there. But one thing I vividly remember that was being discussed, debated fiercely, and agreed upon in the first meeting of the working group was that we are talking about IS 456, and we are all proud of IS 456. So we are not going to bring in a new code, which probably was easier task by borrowing things from other international codes. We are going to retain IS 456 the way mostly it was, of course, at the same time dealing with this huge new scope that we are looking at. So that was the basic principle on which work began on the revision of IS 456. In this regard, I will quickly touch upon these aspects in this presentation, but the first one, I will take the liberty of touching a bit on the background, because as Professor Murty reminded all of us, 78% of us are probably just as old as the code is, and probably younger than that. So it will be good to have a quick recapitulation of what IS 456 really is. So the first publication came out in 1953, and it was essentially for building construction. Of course, working stress method was used, which was improved in 1957 as the first revision. And in those days, only nominal names was done. In the second revision in 64, 456 really was opened up for all kind of concrete structures. And very interestingly, in that revision, ultimate load method was introduced, and though in the form of an annexure or appendix D. And this is where it all begins really for us even today, because this is a quote from the 64 version, which says the concrete stress block. Until then, we were doing working stress methods, so we never bothered about talking about a stress block. But here it said that it could be assumed to be a rectangle, trapezoid, or any other shape. But then we chose to use this very familiar parabola stress block, and it has many there are many good reasons why this is a good choice. We will not go into the details of it now. So essentially, this was the stress block that was used for the ultimate load design. Then, of course, 1978, there were a lot of changes that happened, and one of the changes was that we migrated from working stress, and possibly instead of going towards ultimate load, we moved to limit state method. And again, there were many good reasons for doing that, and even today it's an important thing. So a lot of changes happened, but this was the key one. And in this, I just want to highlight these two statements. That is, it acknowledged the importance to revise the reinforced concrete and the pre-stressed concrete codes simultaneously. And this is exactly what is being done even now, right? So that's one part. And second part is that now with limit state design, the design calculations are more involved compared to what they were in work while using working stress method, and therefore design aids were prepared. So that again, as Prof Murty pointed out, there is this plan of bringing out the white book and the orange book and the green book. So essentially, we are sticking to that philosophy so that the engineering community benefits most. Now, coming back to this design stress block, so this is effectively the design stress block which was used. So with partial safety factors, this was the parabolic portion and the straight portion, and the strains at which the peak strength was attained was defined as 0.002 and 0.035. All of us are very familiar with this. And so this is how the design was done. For normal stresses, this was the stress strain curve, but for shear, which is shear and torsion, we still went ahead with a stress-based approach. And then a lot of effort was put on durability and fire resistance in the 4th revision, which came out in 2000, which is 2 decades from today. But in the 2000 version, structural design provisions were not significantly touched, rather they were very minor, one change that was done. So effectively, what we are looking at is that the structural design provisions which are being relooked at now, today in 2020, are essentially 42 years old or even more. And that is a issue that we need to look at carefully. What the 4th revision did was it acknowledged that probably by then a lot of higher grade materials, particularly concrete, came into the market, and the code allowed use of up to about M80 concrete. But then in a small note, it says that for concrete compressive strength greater than M55, design parameters given in the standard may not be applicable. And this led many engineers to fall back on other international standards because our own IS 456 did not provide solution. That was one part. The other part is a lot of people did not pay attention to this and went ahead designing structures with the same stress block, even for higher grades of materials. So both things happened in the last 2 decades. So this is what we saw IS 456 covering all 3 methods, and some of us who are also familiar with other international codes, we know that there is a 4th one, which is the LRF method of design. So one of the first things to decide was, what is it that this new revision of 456 is going to bring in? The decision was to continue with limit state design for very good reasons that we have. And so the basic framework of the code remains unchanged. So we are going to use with the characteristic, values, and then have partial safety factors for concrete and steel. And now in this gate, you will see 2 types of steels being talked about in the code, of course, reinforcing steel and prestressed steel. But the interesting thing is the decision was to continue with the same partial safety factors for the purpose of structural design. Although there might be argument that today we have better quality control and so on and so forth, but still we are going ahead with this. Now, having agreed upon that, the next issue was in design, we talked about limit state design was based on the limiting strain value. So what are the limiting strains? So earlier we had these HOISD bars, which was part of 1978 version of the code, and SP16 charts and everything use this. So we are going to continue with that for the purpose of design, the design curve is not going to reflect any possible strain hardening. That is another issue that was decided. But the question was, what is the limiting strain? So for this HOISD or CTD bars, they did not have any definite yield point. So 0.2% group strain was considered as the limiting strain. Even for mild steel, the same thing was used. And today we have a third group of reinforcing steels in the market, which is the TMT bars, whose stress strain curve, if is watched closely, reveals that of a mild steel kind of a thing. So essentially, it has this very elastoplastic behavior, at least near the yield region. So what is agreed or decided is that we're going to use an elastoplastic idealization for the design stress strain curve of reinforcing steel, which is probably long due. And so now, with grades of steel as high as Fe600 being admitted, these are going to be the limiting strains, which are going to be very critical for design, as we see. So that is for steel. Now for concrete, what is it that we are going to adopt for concrete? The issue in the previous version was that this stress block was given and the strain values were fixed at 0.002 and 0.035. These are the strains which were fixed for all grades of concrete. Now, as shown by Mr. Arora, it is going to be grade dependent. So there are many literature on this. This is just an example, one example out of which it shows that as the grade of concrete, the cube strength increases, the ultimate strength decreases. And this is the kind of variations. There's a slight nudge, and thereafter it goes up. Most in the initial days, most experimental results were up to about M40 and 60 grade of concrete. Of course, today we have higher, experimental results for that. But essentially, that is extrapolated, or if it is extended, this is how the ultimate strain is seen to reduce. And so this is essentially the nature of the stress strain curve of concrete if testing is done. So the ultimate strain reduces with increasing grade of concrete. But the interesting fact is the strain at which the peak stress is attained increases. So the earlier stress block which used 0.002 and 0.035 as the fixed values are now have to be relooked at because of this particular aspect. And that is why, based on a lot of looking at test data which are provided, available, and other things, this is how the stress strain curves are defined, that uniformly from and the ultimate strain two are going to become particularly the second one is going to become crucial for the design. So what is the stress? So this is the design stress strain curve. The expression is simple. Now here is another aspect that many codes gives a different power equation. Flat do that? Do we adopt that? Probably it will be simple to give one simple expression for all of it and just use the quadratic equation which was there originally, and instead of changing the power based on grades. So at least one thing is taken out of the equation. But this is done considering the fact that the ultimate strength capacity are more or less maintained. So that is how this values are arrived at, so that the ultimate estimate of strength is not compromised or not significantly changed, but this is how the strain values are decreasing. So for most of us, we have to now migrate from these fixed values of 0.002 and 0.035 to different values based on grades of concrete. And as Mr. Arora highlighted, that at M100, eventually these two values coincide. Now, since the stress block is changing, that is the ultimate strain is changing, the stress block parameters would also change. So for all of us who are very familiar with 0.36 FCK and 0.42 or 0.416, obviously the stress block parameters are also going to change. And it's very simple calculation expressions you will see coming up, and it will be given. So in today's context, it's not a big thing because seldom design is being done by hand. It's some form of computer program is written or in spreadsheets. It's very easy to incorporate all this. So that is this. Now, there's an important issue of harmonizing the code for many different things. And so we looked at the nomenclatures. We all know that for beam sections, for instance, there are three types of sections: over balanced and under reinforced. And in limit state design, we used limiting strain based definition to define this. So under reinforced is one where the tension steel reaches the limiting strength, which is this epsilon limit, before the concrete crushing strength, concrete in compression. So essentially, if you look at the response of the moment curvature behavior of a reinforced concrete section, these are the salient features: cracking, yielding, spalling, crushing, and probably there will be buckling of compression reinforcement thereafter. But for our interest, these are the important aspects: cracking, yielding, and crushing. And this response, if we are to kind of even idealize, then we see that there are two aspects that we need to look at. Two levels of strengths one corresponding where the yielding, significant yielding is happening, and we design under reinforced sections for that, to steel, for the steel to yield. And then one corresponding to what we call the ultimate strength, which is corresponding to crushing of concrete, or what we call the secondary compression failure. And similarly, the deformations or the curvatures. So there is an effective yield deformation or yield curvature and ultimate curvature. So now you see that the focus is getting shifted from strength alone to the entire load deformation response, so that we look at both strength as well as deformation. Now, in terms of strength, the IS 456 or design, structural design in essence is about providing adequate strength capacity. And so we used the definition of ultimate strength corresponding to secondary compression failure as the definition of design strength. And the objective was that that estimate should reasonably agree or match with test results. So for shallow beam sections, that worked very well. And when the full stress block is mobilized, we get a strength estimate of strength, and which matches very closely with experimental result. But the question is, now we are going to have structural walls, and most buildings, most multi-story buildings, they necessarily have structural walls. Is it really possible to mobilize the full stress block in such long RC sections with steel distributed on the other two faces? In shallow beams, the steels are distributed on the highly compressed edge and the tensile edge, whereas in these kind of sections, steel is distributed along the length. So is it really possible to mobilize this, is the question. Just as an example, if we consider M60 concrete and Fe600 rebars, of course, we get a lot of other combinations also. And here what you're seeing is moment curvature, a normalized curvature in terms of WD of a W reinforced 300 by 600 section and 300 by 1800 wall section. Needless to say that the wall section has higher capacity, which is okay. But the interesting thing to note here is the difference between the point where first layer of steel yields, starts to yield, and the secondary compression failure point. This margin for this particular example is 52%. Now, this will vary depending on the percentage of steel, the grade of concrete, the grade of steel, the dimension of the wall, and so on and so forth. But what is being seen is that this margin can vary anywhere between 10, 15% to 50%. So what is the problem? There's no problem with this. We have higher strength capacity. The problem or the concern is that if that point has to be reached, it means that the strain in the steel has to reach a very high level. Typically in shallow beam sections, this strain would be 1.5%, 2%. What is the problem with that? Because our reinforcing steel has much higher strain capacity, elongation capacity. The problem is with cracking. With very high strain in the steel, there will be significant cracking, and that will lead to lateral deformation, reduction in stiffness of the structure as a whole, and overall safety will have to be assessed in a completely different way. So while it was okay to use this strength for shallow sections as the definition of design strength, now it seems that it is probably not so appropriate to use the strength corresponding to the ultimate level for these kind of sections. So we need a consistent approach of dealing with this, and that is where the concept of limiting strength is introduced or proposed to be introduced in this version, where we go back to the definition of an under reinforced section, where it is one where the tensile steel yields before concrete crushes. So if we take that as the basis, then it is consistent, and that is being proposed here. For a section like this, which is that level of steel is another aspect which can be an effective depth can be used to define that. But essentially now we are moving away from the ultimate strength as the design strength to a concept of limiting strength. And these are the parameters, stress block parameters, which can be computed based on the strain, the maximum compressive strain in concrete, not a major issue. So that is about the strength. So we are now going to look at limiting strength, which is going to use the partial safety factors, as we discussed, for the estimation of design strength. But then if the partial safety factors are going to be removed, then we get what we call a nominal strength, which is based on the characteristic strength, basic strength, minimum specified strength of the materials. But then we know this so-called characteristic strength is the 5%. That means it is expected that in 95% of the cases, actual strength of the material will be higher. For instance, if you go and buy Fe 500 steel from the market and come back and test, you are supposed to get a strength more than that. So let's say you get something like 560, which is 12% more. When you say M30 concrete, actually if you go and test, you're supposed to get an actual strength higher than that. And that means there is what is called an overstrength. Now, why am I talking about these three levels? So there are three levels of strengths: the design of the limiting strength, the characteristic strength, and the overstrength. The new revision, intends to bring in these to say that the limiting strength is necessary for design of new structures, but at the same time, the overstrength is important for assessment of existing structures. And so, for the first time, the code is probably going to explicitly talk about both design as well as assessment, because that is also a very important exercise in today's context, that we have a lot of buildings which have already aged, and so this assessment is going to be an important part of civil engineering profession. So this is important to recognize at this stage itself. So we have three levels of strengths and two levels of demand. So that is the capacity, this is the demand. Of course, we have the factored loads and unfactored loads, which is going to be used for serviceability checks, and factored loads are going to be used for safety, the structural design safety, where these load factors will be used. These are the different loads. Prof Murty has already shown 10 force type loads and 6 displacement type loads, and these are the basic load combinations. So we have 16 basic load combinations, but actually there are 19. And this table gives the entire spectrum of combinations of loads that might be relevant for a particular design. As already pointed out, are all these loads to be considered in all cases? Answer is no. Obviously, only the relevant load cases will have to be considered, and then this gives the combination that needs to be taken care of by the designer. I'm not showing the load factors and all those for so many cases. So that was for the load. Then there was another issue, which is the essence of design. So we have for the basic quantities, let's say if we look at bending moment as an example, M represents moment. We all know that. Essentially, this represents the unfactored. That is the intent. But when it comes to for safety design, then that moment demand will be called MD. So this is the design moment or the demand. Whereas for the capacity, it will be called M sub A to explicitly denote that we are now talking about the limiting moment capacity of the section. And of course, there will be overstrength moment capacity. This is done so that we don't get confused with when we say PU or MU, we don't know whether it is the factored axial load or the design axial capacity, whether it is factored moment demand or is it the moment capacity. So that confusion will not be there anymore, hopefully. So with that in place, now we move to analysis. And analysis is going to be important, as always, for purpose of design. So what is the basic philosophy? The philosophy is that we try to ensure that the structure or structural element or whatever it is has capacity more than the demand that comes. For instance, in case of a bending moment, now we'll be writing ML should be greater than equal to MD, the design moment, which is the demand. But then these words, capacity and demand, are only estimates. So for instance, if we look at demand, if we look at that, we can have an upper bound estimate of demand or a lower bound estimate of demand. And this is where design codes have to come in and specify how these quantities are estimated. For instance, when you talk about doing linear elastic analysis, we get an estimate of demand, let's say bending moment in a column. But we all know that under certain situations, if we do a second order analysis or a full nonlinear analysis, there can be additional moments because of P delta analysis and effects. So one is the linear elastic analysis. Then we should do second order analysis where there is an approximation in terms of giving additional moments. All of you will recall that for design of, for instance, long columns, we add a additional moment. So that will be continued. Or in special cases where full nonlinear analysis is possible, demand can also be estimated based on that. So that process is going to continue as it was there in the previous code, and it is going to be decided based on the stability factor, which we know that if it is less than a certain value, then linear elastic analysis is okay. Otherwise, it can be done in two stages. One is linear analysis with the additional moment, or a full nonlinear analysis. So that is going to continue as is currently available. But this kind of analysis is relevant only when we have frame action flexure dominated behavior. And there are a lot of concerns in the industry today about design of sections where the classical Euler-Bernoulli hypothesis doesn't work. For instance, pie caps and corbels and so on and so forth. So for those kind of situations, IS 456 committee intends to bring in strut and tie analysis and design method for the first time. Although it was mentioned in the previous code also, but probably this time it is going to be brought. So just to summarize, conventional analysis, we do finite displacement based structural analysis, which we do. Most computer softwares follow this. The matrix method of analysis, which can be linear plus additional moments, or a full nonlinear analysis considering geometric nonlinear. But while we are going to rely on computers for doing our structural analysis, it's important not to lose touch with the basics of engineering. That is where a lot of the simplified analysis which was already there in IS 456 are going to be continued. For instance, moment coefficients plus for slabs on stiff supports are going to continue. The distribution factors, shear coefficients, moment coefficients, effective length factors for columns and walls are going to continue, because that really gives a feel for the the behavior. It's not going to be coming out of a computer software and you just blindly take those numbers and go ahead and switch out the design. This gives an opportunity to understand structural behavior, and so it is important that these are continued in the current revision, and they are going to be done. Of course, pre-stress concrete is also going to be part of the code now, and so analysis of PT systems and are also going to be included. One particular issue which Prof Murty touched upon is that, for instance, we have a building or a system where some part is going to be PT. A designer designs the building, details the building, that part is done. The PT part is left for somebody else, and they come and they do give a design, and then the whole thing is constructed one after another. But the fact is, when this, let's say this slab is tension, all the columns and the beams are going to have a relative deformation because of that. And this holistic analysis is not being done today. And so probably the code is now going to insist a wholesome analysis rather than analysis and design by parts, that somebody does one part of the design, somebody comes and just adds another part. So this is something that we need to watch out for in future, and we should be doing it. Talking about continuing with analysis, now in the in the previous code, the code stated 3 options for modeling properties. It gave cross section properties, transform section properties, or crack section properties. But then the crack section property had to be calculated, and nobody was sure how to do it, what to do. It would change along the with different elements, so nobody did that. Now, in line with what other codes are giving, this is going to give this crack section properties, which are to be used for your load and analysis of frame structures. Watch the difference in the effective section properties for beams and columns when it comes to seismic load. So this will change the load sharing significantly. More load will go to the columns when you have EQ as a governing load combination. Talking about strata and tie, yes, now some provisions are going to be provided. Of course, these are situations where multiple solutions are possible, just like plastic analysis, strata and tie model. So it will now become the responsibility of the designer to investigate all probabilities and then come up with a design. The code will provide basic norms for choosing the strata and tie model and designing the struts and providing the reinforcements. So that will be provided by the code. Now I'll quickly move on to the design strengths of the thing. So these are the basic design property design parameters that are material properties that are used in design, and Mr. Arora showed most of it. The very first thing is this: we in India are stuck with this cube strength and then conversion back to cylinder strength. So cube to cylinder conversion, strength conversion is something that we have to live with. But now watch out that one value, the classical value of 0.8 is going to be used, continue to be used for design. But for assessment, now we have more rational data to be used based on experimental data that is available with us. So this is a slight change from what we have been doing earlier. And because assessment, as I said, is going to be an important activity for engineering community. In terms of modulus of for steel, reinforcing steel, it will be 200 GPa as usual. Prestressing steel, 195 GPa. Mr. Arora showed about the modulus of concrete. Now here again, there's a slight change. All of us are very used to 5,000 root FCK and 5,700 root FCK. But now we are going to see a slightly different expression for modulus. We will get used to it. This is based on a lot more experimental data, which is now available with us. However, when it comes to probably as of now, the code is going to fix it at M40 and P500 steel just for the want of reliable experimental data. Probably as and when more experimental data is made available, we can have some revisions to this. But for now, even if you are going for higher grade concrete and different higher grades of steel, we will stick with these for the purpose of structural design. But significant, quite a new change is in terms of how we design for shear. And so here what you see is the definition of tau C max. All of you will remember table 20 in the current IS 456, which gives the tau C max as a function of grade of concrete. Earlier it was pegged at M40. Now we are able to move it little further up to M60, but beyond that, again, it is being made fixed because we don't have significant experimental data to suggest that we can go higher. So that is it. That is about how expression is being provided. precisely with the factor of safety which is embedded in it, and it looks like this. So essentially it is 0.36 cube root of TTFC. All of you will remember table 90, which is Tausi values on the stage of tension steel and grade of concrete. So here stage of tension steel and grade of concrete, but the expression is this with 3 modification factors based on the type of aggregate, the cross-section size factor, and the cross-section geometry. So now it is more explicitly given, and anybody can quickly include it in a spreadsheet for design. As usual, now since ET is also part of it, and for columns, and walls where compressive loads will be present, the same modification enhancement factor of delta is going to be continued for the shear capacity, shear strength capacity of concrete Tausi. So effectively, if you see this graph, this gives a perspective of it. So the dotted lines are what we had from the 2000 version, IS 456-2000 for one scale. It's a function of Tausi is a function of tension scale. Now this is what we are going to have. So we probably are saying that we have a little more confidence in shear capacity, and so that is going to be useful for our design. As far as tensile strength is concerned, it is now going to be 0.5 square root of FCK. We have to get used to these little changes because this issue of mean versus characteristic plagued us a lot. And the earlier expression was probably more towards mean value. We wanted to bring it down, make it consistent, and bring it down towards characteristics. So, but still it is only mean minus sigma. So it's going to be 0.5 square root of FCK. As far as compressive strength is concerned, we are going ahead with the same thing. So 0.45 FCK is going to remain as 0.45 FCK, except that the strain limits are now going to change. Strength limit is not changing, strain limit is changing. Now, for structural design, as Prof Murty showed, now we are going to have 6 limit states, the first 2 being the limit state of safety and limit state of serviceability. Then we have durability, which is a very important aspect, and then robustness, integrity, and restorability. But all these shall be looked at only when we don't have instability in the structure. So only when there is no chance of overturning, no chance of sliding, no chance of flotation, subsidence, and elastic instability. So these are the first checks as far as limit state of safety, serviceability, and so on and so forth as required. In this regard, as it was already there in the previous code, for initial proportioning, some basic guidelines are provided. One is with respect to absolute sizes, and then the relative sizes in terms of L by D and other aspect ratios. Similarly, as before, guidelines are provided with respect to reinforcement, minimum and maximum. And now an attempt is made to bring all of it in one place so that if these basic guidelines are followed, you already have a design, a structure, right? And generally it is believed that if these guidelines are followed, the limit state of serviceability will be satisfied. Because there are checks to be done, but in general, it is expected that limit state of serviceability will be satisfied. So the whole purpose of analysis and design thereafter will be to improve, to economize, and so on and so forth, to come up with a more optimum structural design, and that will be based on analysis, design, and detail. So that is the second part of it. So what are these basic guidelines that are provided? In terms of absolute values, minimum member sizes are provided. So you can see slabs, beams, columns, structural walls. This is an important thing that was discussed, deliberated a lot. The concept of structural wall, when required as a lateral load resisting system or as a part of the structure, Professor Murty touched upon, we can't have single layer of curtain. Now to have a 2-layer of curtain, there is a certain minimum thickness that needs to be provided. That is something that we need to watch out for. Of course, this is only based on minimum member sizes. From structural point of view, there are durability and fire requirements also over and above this. But then for simple residential buildings, let's say up to 3 stories, that was discussed. Some of these items are, there are relaxations which are provided. For instance, beams can be 200 by 250 and so on and so forth. So these kind of guidelines are provided. Then with respect to fire resistance, there are guidelines for minimum member sizes. This is a table which is slightly older because the new discussion is that NBC mandates that all structures be designed for minimum 2-hour fire rating. So we might as well remove the first 2 lines from the table. And this is another aspect that is being debated right now. But effectively, we'll have a table which will give minimum member sizes for fire resistance point of view also. Just like member sizes, we have cover. Arora ji talked about cover and how it is arrived at in detail. I'll just show the final, kind of answer. Essentially, the summary is this, that the nominal cover is being defined based on 3 requirements. One is the structural requirement, that even if this cover concrete falls off, the member should not lose significantly its load carrying capacity. That's the basic premise. Then, of course, there is the durability requirement and finally the fire requirement. So from structural requirement, these are the nominal covers which are recommended. Then we have durability requirements for the mild, moderate, severe, very severe, extreme exposure conditions. And then again, we have requirements of nominal cover from fire safety point of view. So these give us the basic dimensions, but then there are relative dimensions which we also need to look at because we do not want too slender or too stocky members to be present in the system. And overall stability is also important aspect that needs to be looked at. So beams, as earlier, are those whose depth by breadth ratio is less than 2.5. Columns are also the same, and structural walls are those which has this depth by breadth ratio more than 4. Now, what about those sections which are between 2.5 and 4? We all know what happens usually, because then they are neither called columns nor called walls. But then since they are not called columns anymore, we generally love to use these kind of cross sections with this aspect ratio because of the minimum percentage requirement that we had. But now code will be very clear that these kind of sections, because it's about the behavior, it's not anything that is in between, neither behaves as a column nor behaves as a wall. So they will be discouraged, but in case we have them, we have to design them as columns. So they will not be treated or considered to be walls, but columns, and be designed and detailed accordingly. In terms of L by D ratios of beams, so we had these provisions for less than 10 meter and more than 10 meter. Slight changes, slight modifications compared if you compare them with what we have currently, but that is in line with a lot of other literature and international codes also. So for slabs, it looks a little tedious. It's now a functional grade of steel also that is being put in, and then these are the numbers, these are the tables, these are the proposals that we have currently. In terms of minimum longitudinal reinforcement, of course, we are going to have higher grades of steel. So again, it is fixed at 0.12% for slabs. But for beams, we will have a slightly different looking expression than what we have currently, 0.85 by FY, which was not dependent on grade of concrete. That was probably because the grade of concrete that was admissible as per the previous versions of the code, particularly 1978 version, was only up to M40. Now we have a wide range, and so it is important that this minimum longitudinal reinforcement is takes care of the grade of concrete and grade of steel. So accordingly, we will have minimum longitudinal reinforcement requirements in beams depending on the grade of concrete and grade of steel that we choose to use. In terms of columns, earlier we had one single value. Again, that was okay in 1978 because we had very little change in grade of concrete and grade of steel. Options were not too many. Today we have a lot of options, and that is where the minimum longitudinal reinforcement requirement in columns are going to go up as we move ahead with using higher grades of concrete. It is important that we recognize the associated effects of creep, shrinkage, and so on and so forth, and particularly the reduction in strain capacity of concrete as we move towards higher grade of concrete. And that is why it is important that we protect our vertical elements in our structures, the columns and the walls, from any damage or failure. Similarly, structural walls requirement is given explicitly now, and footings and rafts are also stated properly so that there is no confusion. In terms of minimum transverse reinforcement, of course, slab doesn't require mostly, except very special cases. But beams, now there is a minimum transverse reinforcement requirement in terms of the quantity of transverse reinforcement. Earlier, we just had, there is a design part which was available, and then we had a minimum spacing, maximum spacing, and requirements, minimum bar diameter. But now there is an additional calculation which will have to be done to ascertain whether a minimum amount of transverse reinforcement is being provided or not. Same is the case with columns. So it is not going to be the nominal ties based on the diameter and the spacing that we usually provided, but more computed value of transverse reinforcement ties and stirrups that will have to be provided. And then structural walls when required. Coming to maximum reinforcement. So this expression looks little, involved, but essentially what it says is what the earlier code also said, that over-reinforced sections will be prohibited. Same is the case now. So the limit for maximum reinforcement is whichever is less, either that for the balanced section or a predefined value. For slab, it is kept at 1%. For beams, it is kept at 2%. And for columns, we'll see this case. So now this is an interesting thing that with different grades of concrete and different grades of steel, we will have requirements of different maximum reinforcement, which will cause things. So an engineer will have to keep an eye on that also. It's not just one single value, because now we have many options of steel and many options of concrete. So that combination is what has to be looked at carefully and investigated, and we will not go with specified single values anymore, because the range is quite large, starting from 415 to 600, possibly 650, and similarly on the concrete front from 20 to 100, possibly in future beyond that. The range is too large, so we need to be careful. We can't be going ahead with one single value. For columns, of course, 4% is generally considered, but to be okay. But then many practicing engineers will say we should bring this down even further. We will be very glad to get such inputs from the practicing engineers, because congestion of reinforcement is an issue that most engineers deal with on a daily basis. So, but right now this is the thing where it is kept. In terms of structural walls, and as you can see, now in this revision, structural walls are brought in the front. Importance is given to structural walls because we have other relevant Indian standards which now kind of mandates use of structural walls in buildings and particularly multi-story buildings, tall buildings. So IS 456 has to be very explicit and be generous in terms of provisions related to structural walls. So you will see a lot of these provisions in the upcoming version. So the web portion, the maximum reinforcement is pegged at 2%. These numbers are all debatable. These are the proposals. They can be lowered, they can be enhanced depending on larger consensus. So do not worry about those. But so similarly, and then we have the boundary elements for which essentially boundary elements are going to be treated more like the columns, and so the requirements are very similar to those for columns. So a lot of details. Quick takeaway for everyone: slab 1%, beam 2%, column 4% as the maximum reinforcement as of now. Easy to remember. Coming to structural safety, so now as far as since we have the design stress strain curve for the normal strain, normal stress of materials defined, all calculations, all design calculations will be necessarily based on principles of mechanics. So equilibrium equations, compatibility conditions, and constitutive relations will be the dharma in all design calculations. Empiricalism will be avoided as much as possible. This is important so that young engineers, students learn the subject and they just don't become engineers knowing how to use a computer software to come up with a design. That is important. And this is going to be applicable for both reinforced concrete and pre-stressed concrete. So as Professor Murty pointed out, the whole thing is going to be elaborately presented so that all the design calculation steps are easy to remember. Now, as far as pre-stressed concrete is concerned, there is going to be change, particularly in terms of the estimates of flexural and shear capacities in line with what has been presented for reinforced concrete. But there are a whole lot of other issues related to pre-stressing, the methods of pre-stressing, and so on and so forth, which are going to be brought in from 1343 with necessary adjustments, modifications, and most of it is being redrafted for consistency so that we have a nice flow of the new IS 456 with respect to this. So to summarize, we have design guidelines. The details I have not presented here because that is not the intent here for this webinar. We have clear guidelines for design for flexure, axial actions, shear, torsion. Shear and shear, there's a modification. Torsional design is mostly unchanged, except that the shear design and flexure design capacities, the definitions of these limiting strengths will now come in instead of the ultimate strength values that we used to earlier use. Then, of course, PM is an important check that will have to be done, which is also now going to be presented. And watch here that when it came to PM interaction, earlier, because the stress block was fixed, had fixed strain limits of 0.002 and 0.0035, the pivot at 3/7, 4/7 was fixed for all grades of concrete. Now, with changing limits of strain for different grades of concrete, it is not going to be so straightforward. So a simplified procedure is being given in the code so that PM interactions are easily handled. You're not sure whether VM interaction and PV interaction can be brought in this time because it needs little more refinement before probably it is introduced. And PVM is something that is not being discussed at all at this point in time. So what are the key changes that are made in this? As I said earlier, the focus is now not only on strain. So until now, when we design, as in a design office, a designer's focus was only on providing strength capacity. Now the focus is going to shift from both design of existing structures as well as on assessment, and that is where the code will help in both the activities, and that is the intent with which the revision is being made at this point in time. Similarly, the focus is not just going to be on strength alone, but deformation also, because we now have the limit states of robustness, integrity, and so on. So it is important, imperative that designers start looking at the entire load deformation relation of a structural element of the structure as a whole, rather than focusing only on strength capacity. So that is going to be a broad change in outlook that is now going to happen, and we engineers will have to adapt to that aspect. Of course, limit states, earlier we used to have this limit state of collapse, particularly for large wall sections. It is not possible to reach that limit state. So when we say, of course, the design objective has always been that limit state of collapse is not reached. But then that is too far away. It will lead to a lot of other associated problems. So the limit state of safety and limit state of serviceability are the ones which we were conversant with. Now we'll have to look at all the others, and that is where we will be focusing on the overall behavior of the structure as a whole, and not just focus on strength. As far as design calculations are concerned, yes, it is going to change not in a drastic way, because we are still going to continue to use our known stress block, the parabola straight format, except that now the strain limits are going to change, and therefore certain calculations, the values are going to change. But that is not a big deal. But essentially that change is going to happen because of the change in design stress strength. And the important concept of limiting strength instead of the ultimate strength is something that we'll have to get used to. As I showed, shear design is now greatly improved, and so we'll have more confidence on that. Now, as I started off by saying that the intent was not to suddenly come up with a code which looks very different and very new. So a lot of items are still retained. They are completely redrafted for a nice flow, but essentially a lot of things are retained. And for instance, simplified analysis is still going to be part of this new code, because you don't want everybody to run a computer program to do small little designs. And that is where engineering sense comes from, not by running computer programs. So these are important. As Professor Murty highlighted, design for shear is still going to be stress-based, but fortunately will be in future we'll be able to move that also to strain-based design. Before I end, I will focus on certain implications of use of higher grade materials, because basic need for this overall or revision a lot of these materials in our daily construction activities. So what are these? What are the immediate ones which we design have in terms of shrinkage, splitting, because when you have higher grade of steel with very high level of stress, what is the effect of that on splitting tensile cracks in concrete? And concrete of higher grades whose strain capacity is less. So there are areas which needs a lot of research or a lot of investigation to be done. We need to understand issues of flexible structures. Why flexible structures? The whole intent of using higher grade of material is to come up with more slender, smaller cross sections. So that is essentially. performance of non-structural, a lot of work in terms of establishing that we have adequate margin against durability. Fatigue is something that we need to think about also in the long term. So just a quick thing in terms of balance section, we remember 0.48 as the maximum depth of neutral axis, 0.48 times the effective depth. Now, of course, with new grades of steel and new grades of concrete, those numbers are not so sacrosanct anymore, but we will have to keep an eye on the different numbers that we get for different combinations of steel and concrete. One very critical implication of the use of these higher grades of concrete, which has lesser strain capacity, as already demonstrated through a lot of experimental work, is this change in ductility capacity of structures. For instance, we can have as much as anywhere between 20 to 40%, probably 50% reduction in ductility capacity. So this is an occasion where we need to really be careful about using this, because it needs re-evaluating our whole design strategy, not just for the regular dead load, live load, but also, let's say, for seismic loading condition, for which basic design is going to be done based on IS 456. This is going to be the mother code always, so it is important. We have to, it has long, far-reaching implications in terms of seismic design also. These numbers, of course, vary with different things. This summary is based on the work that is done for shallow beam sections with 415, Fe 500, 550, 600 grades of steel with 0.5%, 1%, and 1.5% reinforcement. So this is something that we need to watch out for. Similarly, one very important discussion that came up during the deliberations were the design for shear. We all are familiar with this expression. Now, what happens when we use, let's say, a very high grade of steel? Fy increases. That will require you to provide lesser amount of transverse reinforcement, or that is thinner, lesser diameter stirrups, or at a larger spacing. Now, the current code, all of you will remember that it has a clause where it says, for the purpose of design calculation, Fy cannot be taken more than 415. And that is going to continue now. So probably there is not so much of an incentive to go and use higher grades of steel, particularly for transverse reinforcements, because that is not something that is warranted, that is desirable. Thin stirrups at larger spacing is not good for structural reinforced concrete and prestressed concrete members. So that is not something that the code is likely to allow. Talking of slender members, when we go for higher grades of steel and higher grades of concrete, essentially strength capacity is more for a given amount of material. And so therefore, for the same load, we will be probably coming up with smaller column sections. We'll be tempted to provide that. What it will essentially lead to in situations is that we will have very high axial stress ratio in our columns, let's say in moment frames. And we all know, we remember the balance point on a PM interaction diagram. Anything above that is governed by failure of the concrete and not yielding of steel. And so they are going to have very little ductility capacity. This is something that we need to watch out for when we use high strength materials for our constructions. Smaller houses may not need use of these high strength materials. So small size columns for design are going to have compression failure as the failure mechanism. Rather, we should larger column size so that the action stress level is within limits, below the balance points, ideal, but need not be necessary for all cases of under all load cases. But if we do come up with slender members, slender beams, slender columns, our structures are going to be more flexible compared to what they are today. And that will definitely have associated effects in terms of lateral drift, vibration, acceleration, and so on and so forth. And more importantly, a lot of effect on the non-structural components that we have today, particularly in commercial buildings, multi-story buildings, and so on and so forth. The cost of non-structural component is huge as a proportion to the structural cost. And so possibly we will be jeopardizing those also. So the big picture here is that through this code, through this revision, an attempt is being made to bring back structural behavior in focus. As designers, we have to always think about the big picture and put structural behavior in focus and not get lost in the details of analysis and design. That is the important message that should be taken from this new revision of the code. It is not designing for flexure, designing a beam, designing a column, but the overall structural design that a designer is usually responsible for. And that is the structural behavior that is important. So in closing, yes, there are some major changes. There are many minor changes, and that is possibly the cost for waiting for 4 decades, 1978 to 2020 we are today, and possibly it will spill over to 2021. As Professor Murty pointed out, an entire generation of engineers were probably are younger than the the structural design provisions that we are currently using, and so that is what is leading us to this situation. If we revise our codes every 3 years, 5 years, probably we would not be in a situation like this that we are in today, and that is where we need cooperation from everybody, academia, industry, everyone has to pitch in, because a lot of changes are happening and that needs to be disseminated. And so this is where it's important that we all work together. A lot of testing needs to be done. Probably we are using scope to go back to classroom and learn the subject once more. Students, teachers, engineers, all of them will have to pitch in and do their bit to understand this new paradigm of design, structural design. This is where we'll have to work together. This is only the beginning. This opportunity for a consultation is a wonderful concept, and we need to not just dwell on the minute details of design. Those are important aspects because that is daily job that we do, but also we have to know and understand and appreciate the overall intent. So I'll reiterate what was said early in the morning. Unless we clearly state our requirements and identify the shortcomings and gaps and clearly state what is required, probably we will not be able to come up with a code, a revision of IS 456 with which all of us will be very happy with. But for that, we need everybody's help. We do solicit you to give in your considered inputs for making this document a much improved, better one. Remember, all this is towards a safer built environment in our country, and we all of us have a responsibility towards that. With that, I'll stop here. Thank you so much. Jai Hind.
Thank you so much, Professor Goswami. It was such an excellent talk, and you took us through the nuts and bolts of detailing, and I was amazed the amount of ground you covered in a short span of 1 hour. So congratulations and thank you very much. And I think what you also did was with such great clarity, you also explained the underpinning rationale, and that is what is causing a problem to all of us, especially in since the last code was published. We don't have an explanatory handbook or even design aids. And I think what you and Professor Murty said was like music to our ears, that we're going to have the orange, white, and green book along with this code. Maybe not along with it, but following soon enough. So thanks very much again. I cannot express enough to all three panelists that we're so grateful to you for having given us such an enlightening time this morning. And colleagues, we will meet again as scheduled at 2:15 p.m. And we shall start the question answer session. So great. Have a lovely lunch, and we shall see each other in 45 minutes.
Largely 1343 is again a capacity code. So what we have taken this discussion to one level up. 1893 will not be combined, but 13920 is open for discussion. The CED 39 Earthquake Engineering Section Committee and the members of CED 2. So we have to discuss this with members of CED 39 Earthquake Engineering Section Committee. That hasn't happened yet. We wanted to see first level zero draft of 456 and see whether it makes sense to bring 13920 in or not. There is a lot of expectation that 13920 should be combined with IS 456. It's not clear yet. We are waiting to do that discussion in CED 39. Let's see what comes out. I'm not giving the answer either way, but I'm waiting to see what the discussion will be in CED 39.
No, that's an interesting information that you've given us. The next question, as you can see, is
second part is that 13920. One moment,
yes,
one moment, Alpa. 13920 will be revised after 456 is revised, so the inconsistencies will be removed in 13920. That is not a worry, okay. But the key issue will be that we will need to discuss whether to merge these two at CED 39 first, get their concurrence, and only then move forward.
Yeah, if you collapse it, then it's getting closer and closer to ACI 318, because I don't think 1893 is part of 318. That's separate. That's part of the ASCE codes. So I think we would very much align with ACI. The one question which has been asked by Manohar about, clarity about when do we define it as a rigid or a flexible diaphragm? Is there any, move in that direction to give more prescriptive requirements? Because I think what is interesting today, as what Professor Rupen said and what you said, and in a way, even what Mr. Aroraji was telling us, is that this is going more towards performance-based. I mean, it's just the beginning. There'll be a lot of prescriptive requirements, but it's the first step towards a performance-based kind of a code. So given that, how open are you to tie in some of the loose ends which exist right now in defining certain ambiguities, because those become a problem in design. And all of these issues, I think this column and shear wall, we've been talking since the cows came home, and there's still ambiguity in that also. So if you could just please take up these questions.
Yeah. Rupen, you want to take that question? Manohar's rigid and flexible diaphragm question.
Okay. I'll start with the extreme. The responsibility of an engineer is to produce a safe structure. Then we don't need any prescription, any code. The code should have just one line. The responsibility of safety lies with the designer. You demonstrate safety. Right? One can do full detailed analysis and so on. That doesn't help anybody by having such a prescription. So there will be, these kind of things. The moment a number is specified, there will always be debate whether that is the right number or some other number is correct.
Right.
So we will have to live with this kind of a scenario where nothing is ideal, nothing is exact. These are all considered values which are going to be used to simplify the whole design process. And so the definition of a rigid versus flexible, the debate can go on. Whether we IS 13920 definition. If we want, we can continue with that. If we want, we can discuss and change that number, that value. But there is no end to this discussions like this.
Okay.
You know, that is my take.
And also the difference between column and shear wall. You know, right now, I think one of the questions which is being asked implicitly is that it is based on geometry rather than the behavior. So is there any plan to change how you're defining a wall versus a column? Yeah. And that also the definition is
behavior is something that the designer will have to understand, feel, see for himself or herself. Code can only prescribe numbers, and that is where we say, okay, column is, if the D by D is less than 2.5 column, if it is more than 4, it's a wall. In between, the designer has to take a call. But the only thing that the code is trying to do is say that it is neither this nor that, but you design it as a column. Behavior is going to be in between.
Let me add this here, that if I look at the clauses that are coming up, the column and the wall will not be designed by any different method. They will more or less go identical method.
Okay.
So this distinction will vanish. The only issue is in our minds, for that minimum percentage, we are playing a game. And that is what we are sorting out right now. But in terms of analysis, in terms of design, there's not going to be much of a difference in time ahead. PM interaction will be done for a wall, it will be done for a column. So that will not be a worry so much for me. I would think that that difference will vanish in this code once you start implementing that. But as far as rigid and flexible diaphragm is concerned, I think in the analysis section, we can add a little bit on rigid and diaphragm, rigid and flexible diaphragms, like we have added in 1893 and other documents.
Yes, yes.
So we can put something in there in that direction.
Yes, that would be good. Shall we skip, because I think this clause 32.5 minimum reinforcement, I think, you know,
yeah. Precast anyway, we are not talking right now.
Okay. The use of punching shear reinforcement. Are you going to allow for? I mean, are you going to give explicit clauses for that, or there's no such plan? So I think that the issue is the flat slabs, I guess, in some ways, because one is not very happy with that kind of construction. What I was hearing both of you say is that, you know, you really want to pretend it doesn't exist, and you don't want to pay much attention, because if you start fleshing it out more, in a way, you're implicitly encouraging it. But the reality is that it's still being done left, right, and center. So would you not think that it would be better to give far more explicit design requirements and detailing requirements than not to, or to ignore it? Yeah.
Yeah. So let me start here. The general impression is that if we say that no more flat slab construction, I think I'll be missing from the tomorrow's morning onwards. So I don't want to do that. So I would say that it is important to have a lot of restrictions if you want to use flat slab.
Okay.
Because flat slabs are known not to perform well. Right. And that is why that may be a direction that we can take, rather than allow free for all, do anything you want with flat slabs kind of situation. That flat slabs don't become something special only in earthquake conditions, but also become special in non-earthquake conditions. And we have to do so. That is what we will have to do. We'll put a thick set of conditions, and only when they are satisfied, you can use flat slabs. That kind of situation may arise because of this indiscriminate, is not looking fair.
Okay.
So we may have to come up with tighter regulations as sought by ALPA.
Okay.
Rupen?
Yeah. So for instance, IS 1893 already recognizes it as a system. So I completely agree that we need to have very clear, provisions for this. No doubt.
Okay.
Okay, great. The next one, would you want to? Sorry. Yeah. Yeah. Can you see that?
You have gone. You have to share this.
I'm sorry. I think the problem was with my screen. I apologize. I have a slow server presently, so apologies to everybody. But so the question which was being asked is that the chapter, the section on the design of corbels and DPs and so on is a bit weak. I think, as all of us would agree about, right? So are you planning to kind of look at that? I'm not going to talk about the crack width calculations and pozzolanic cements and so on, because I think that is being really addressed very comprehensively. I think Aroraji's team has really put in a lot of effort. But the other issue which people are talking about is this problem with inadequate requirements in the anchoring in concrete. And I think this was echoed in a lot of email discussions we had on SEFI. So your thoughts on it?
Can you say it again?
So the question is about the provisions for anchor.
High volume flash, you're talking this thing? High volume flash?
No. So okay. So what I was saying that actually the issue about pozzolanic cement based concrete, I think that you are touching very comprehensively, right? So I'm not so much worried, but maybe you want to expand a little bit, Aroraji?
Pozzolanic cement, in fact, I have explained that high volume flash concretes as such we are not permitting unless until we go for the detailed testing on acceleration, corrosion testing and all. Otherwise, we have limited up to 35%.
Okay. So
beyond that, the issue of carbonation comes in. So, but if you are using high strength concrete, but then when you use high strength concrete, normally the flash is already limited. Right. So this was discussed and it was decided that it should be limited to 35% only.
Okay.
But in case of non-enforced concrete, you can always use high volume flash concrete in case of roads and other things.
Right. Okay, great. So Professor Murty or Professor Rupen, would you want to talk about, needing to expand on the recommendations for corbel and deep beam design, and also providing a more expanded section for anchoring in concrete?
Yeah, Rupen.
Yes, I personally, would like to see this happen, because for this anchorage, we have not paid attention, and every time you are having to fall back on international codes, particularly SCI for this. So this is an important thing, particularly for have this issue. So personally, I completely agree. We should have this. So this is what happened. We are already, counting items